Yeah, very good morning, everyone. Very warm welcome to the second day of faculty development program on renewable energy. On behalf of IGEN and Panimalar Institute, I warmly welcome everyone to this session. So, still 2 minutes to go. We will start, please start at 10 o'clock. This 2 minutes we are giving for everyone to align yourself. Yes, we have received quite a lot of feedbacks yesterday, and there are many watchers. Yes, thanks all for your both positive and negative feedbacks. Definitely, positive feedback motivate us, and negative feedbacks ensure us we are correcting ourselves to deliver what's the quality which you are expecting. So I'm giving 1 more minute for all to assign, and we will go ahead with the live session sharply at 10. And those who are not really, join the WhatsApp group or a Telegram group, I will give a quick instruction. Go back to the previous day session, which is already available in YouTube channel. There you will be able to find the link for joining in the WhatsApp group and Telegram group. So, I request all of you to, join in the WhatsApp group as well as in the Telegram group, so that even if you missed out because of poor internet connectivity or something, you will be able to still get back the sessions and feedback link. So in order to get the feedback link on time, let me share the screen as well to just to tell you. If you go back to the yesterday link which you are seeing, correct? Yesterday you have watched in live. So if you go to that video which is available in the channel, right? In that video description itself, we have given the link for joining WhatsApp group and Telegram group. Request you to join in any one of the WhatsApp group or a Telegram group so that you won't miss out the feedback link. Anyway, we have made an alternative arrangements for sharing the feedback link at 12:25, even if the session extends. But we don't want to take any second chance. So please ensure that you are joining in any one of the WhatsApp group and the Telegram group. Yes, time is sharp 10. Let's go. At least we will try to maintain the time today. Once again, I warmly welcome on behalf of IGEN, the Institution of Green Engineers and Panimalar Institute. We warmly welcome you all for this 5-day workshop, 5-day faculty development program on renewable energy resources. So, we have kickstarted yesterday, and we are going ahead with the 3 more days to go. So, let me start introducing the topic, what we are going to see, and probably, before introducing the first speaker and everybody. So let me give an overall view of all the 5 days, what we have planned. Then I will exclusively talk about today. Then, I will move forward. So once again, I warmly welcome everyone. Wish you a very good morning, and hope definitely you have enjoyed a session yesterday. And I believe you definitely enjoy a session today as well as in the upcoming days to come. Right, so let me go ahead. Let me share my screen again. So let me first start with the 5-day agenda. So yesterday, Unit 1, we have covered the introduction of the renewable resources. Today, Unit 2, we are covering about the wind energy conversion systems. Unit 3, that is a solar, which we are covering on tomorrow. Unit 4, that is biomass, which we are covering it on Thursday. And Unit 5, that is a hybrid and all other renewable resources, which we are covering it on day 5. So this is the overall agenda, which you might be aware. So means we are covering from 4 different aspects: the academic view, industry view, employment view, and research view. So every day there will be a speakers from an academic view to just give a highlight of what that subject covers from an academic perspective. And second one, the speaker is from an industry. He is going to explain what's in this subject from an industrial perspective, or how this subject is applied for a real-time scenario on a day-to-day life. And third view is going to talk about what are the employment opportunities which are available. So that's what even yesterday also we have received some comments from the students and faculties. I believe what's the use of studying these subjects and how to get a job. Yesterday Sendil sir has joined, but unfortunately he couldn't continue. But definitely that's the real reason why we have moved this employment view to first session today, right? And research view, that's what we are going to cover. Let me move on to the today's focus. Yes. So today's second day, we are going to talk about wind energy conversion systems. We have 4 eminent speakers. against yesterday, means where we have started about with respect to the academic view, we are going to start from the employment view, because many people and the participants has put up the question like, means what is it? Whether by means of studying this subject, shall we get a job or not? So means we will start with an employment view that's going to be handled by Dr. Sri Rajab Balaguru. He's an assistant executive engineer in Tangentco. Then that will be followed by engineer Amuda. Amuda Sia, she is the manager power system studies at Power Projects. And then, I mean, what to say is, we have an eminent speaker, Dr. Uma Shankar. He's an associate professor in Renewable Energy Lab at Prince Sultan University, Saudi Arabia. He's going to talk about the academic view. And finally, we have an eminent professor, Dr. N. Amudan. He's a professor and head at Rajarajeswari College, Bangalore. And he's going to talk about the research view. That's the overall schedule. And yes, thanks to quite a lot of feedbacks on yesterday regarding the timings, we will try to maintain the time possible. But even if the session extends, you will definitely get the feedback link at 12:25 sharply in both your WhatsApp groups and Telegram group, in addition to YouTube link. So, I mean, I once again request you to go back to the yesterday's video. If you have not really joined in the WhatsApp group or in the Telegram group, I request you, all of you, to join in the WhatsApp group and Telegram group. Even if you miss out YouTube video because of internet connectivity or something, you will get this feedback link at 12:25 in WhatsApp group and Telegram group. So that's the quick introduction. So let me stop there. Yep. So thanks a lot again for joining. And now I request Lavanya madam to introduce our first speaker.
Yes, sir, with a very good pleasure. A very good morning to one and all present here. I'm really privileged in introducing our first speaker, Engineer Sri Raja Balaguru. He is working as an assistant executive engineer in Tangentco. He worked as an assistant engineer in Ennur Thermal Power Plant Station for about 3 years. He worked as assistant engineer in the area of substation erection, commissioning and testing, with a lot of experience in cable laying and joining of 33, 110 and 230 kV substations. He has a lot of experience in the area of SAP and ERP projects. He also worked as assistant executive engineer in non-conventional energy sources, renewable energy generation, real-time monitoring and solving the issues. Added to it, he is a member in Institution of Engineering and Technology, MIET, and a member in Institution of Engineers, MIE. So such an eminent person is more suitable to give the employment view of wind energy. Sir, please, the session is yours.
Balaguru sir, you can probably unmute yourself and you can talk. Kindly unmute yourself.
Okay.
Perfect.
So good morning, everybody. Okay. So the employment opportunities and the challenges in wind energy. So this need of the hour. So at present, this time we need more opportunities in this case. Here we'll go one by one. So what are all the contents? Basically, what are all the renewable energy technologies? So wind, solar, biomass, hydro, wave, and geothermal energy. But predominant one is wind and solar is the predominant one. So everybody knows that. So that is the renewable energy technologies. But here the government of India has scaled up the target of 175 gigawatt by the year.
Sir, sorry to interrupt. Let me request Durai to share the screen.
Yes, sir. I'm starting to share my screen.
Share.
Yeah.
Okay, sir. So probably you can watch that slides and which you can.
Yes, exactly.
Yes, sir,
Exactly.
please.
Yeah, yes, sir. You can proceed, sir.
Okay. So the employment opportunities, and this is the topic today. So employment opportunities and challenges in wind energy. Before moving on to this, what are all the renewable energy technologies? So that we have to know. So wind energy, biomass, solar, hydropower, wave energy, geothermal. There are a lot of renewable energy technologies. The predominant one is wind and solar is the predominant RE technologies. And we have, next slide, next.
Yes, sir.
So this is the, okay. This is solar, biomass, wind energy, hydropower, wave, and geothermal. So these are all the renewable technologies. So most of you know that. But here, the predominant one is wind and solar. So in India is concerned, we are a leader in this in a global scenario. So the government of India has scaled up the project of 175 gigawatt by the year 2022. So you can see this. So next slide. So the government of India has scaled up the target of renewable energy capacity to 175 gigawatt by the year 2022. So which includes 100 gigawatt from solar, 60 from wind, 10 from biopower, 5 from hydropower. And apart from that, mainly the government of India is concentrating on this solar, because solar from the ITA to any even degree or a master degree, we have a lot of employment in this solar particularly. And I'm not talking about particular solar, even wind also, all renewable energy. So this 100 gigawatt is further classified into 40 gigawatt for the rooftop solar and 60 gigawatt for the large and the medium scale project. So this is one hand. So one hand is we have a 175 gigawatt. So this is the national target. We are marching towards the national target. So this is one thing. On the other hand, India's target on carbon emission. This is very, very important. So MNRE framed that the carbon sink for this also, the carbon sink target of 2.5 to 3 gigatons of carbon emissions. So we have to sink this one through additional forest and tree cover by 2030. So this is again another target we have. One thing is this 175 gigawatt for 2022, and see, you have a lot of renewable energy projects. The government has framed a lot of renewable energy projects, including the solar parks, onshore, offshore wind energy, energy storage. So a lot of projects government has framed, and for that, that is one part. So 175 gigawatt by 2022, this moved on to 450 gigawatt by 2030. So the target has moved. They have increased the target. So 175, then 225, and now it is 450 gigawatt by 2030. So similarly, the carbon sink also, we have to reduce the carbon sink. The emissions should be reduced. So carbon sink of target of 2.5 to 3 gigatons of carbon emission by providing the additional forest and the tree cover. And also, India has committed this GDP to 33 to 35% by 2030. So GDP, gross domestic product. So that is that measures the rate of how fast the economy is growing. So we are around at this stage. This time we are around 7 to 8% of GDP. So yet we have to go for 33 means we have to go by 2030. So this is one thing. On the another part, what is that the non-based fossil fuel, I mean renewable energy, 40% so of the installed capacity by 2030. And Tamil Nadu is one of the predominant leader of wind energy, particularly. So this 40% Tamil Nadu achieved already. So that is another remarkable one. Tamil Nadu is concerned in India. Tamil Nadu, we have a lot of opportunities, particularly for the wind. So Tamil Nadu is 1/3 of renewable energy generation. If you take the India whole country, so we are the 1/3 of generator, Tamil Nadu. So which is almost around 25 to 30% of wind power we are producing, wind power alone. So this is the case here. So this is the target of carbon emission. And you can see this has India has committed in the sense to reduce the carbon emission. In 2015, the COP alliance between the pact between signed a pact between India and France. So India and France signed a pact, not only, and other all rich renewable energy countries signed a pact of two target. One is 175 gigawatt by the year 2022. Another one is the sinking of carbon of 2.5 to 3 gigatons of carbon emission. So this is the scenario, the sign, the pact for ISA, International Solar Alliance Pact. So that is the story of this target, how we are fixing the target of national target, that and all. And so next slide. Next. Next. Can I move to next slide, please? Move on to next slide, please. Duray, can you hear me? Yeah. Okay. So you can see in this slide, see here, India, the thermal generation and hydropower, renewable power, nuclear. So you can see that renewable power is 23% in India. See, but if you take Tamil Nadu, see the renewable is 43%. That means the Tamil Nadu has reached that what we have committed in the Solar Alliance, that is 40%. So here it is 43%. That means in India, Tamil Nadu is the highest wind power producer. Renewable. If you take a renewable producer, Tamil Nadu is the highest renewable producer, as well as the wind is the highest. So first in India, highest wind producer. Next.
Yes, sir. Yes, sir. Wait a minute, sir.
You just move on to that.
Yes.
This India as one of the global leaders. So India has emerged a global leader in the country. We are fourth in the world wind energy capacity, fifth in the world solar energy capacity, and we are the rank of fifth in the world total renewable energy capacity. So that is the today's scenario. One thing is we are marching towards 175 gigawatt. That is one different thing. And next is the renewable energy. The renewable energy scenario. We are fixing the 175 gigawatt. That is one thing. But here today, what we achieved is 87 plus gigawatt as on 30th April 2020. So you can see this. The wind power is 38 gigawatt. So because 60 gigawatt is the national target and solar is 100 gigawatt. So I'm taking here one wind and solar predominantly. So wind is 38 gigawatt and solar is 35 gigawatt. So which means that the wind energy capacity in India has increased 1.75 times in the last 4 years, and the solar is drastic, has increased more than 11 times in the last 5 years, from 2.6 gigawatt to 28.18 gigawatt as on March 2019. So this source is taken from the investindia.gov. Next. So wind energy. So wind energy is concerned. So India is the predominant leader in wind energy. Particularly the two rich wind energy state in India is, one is Tamil Nadu, another one is Gujarat. So we have in Tamil Nadu 8,500 megawatt installed capacity in Tamil Nadu. So this is in only state share. If you take a central share also, like a CTU, so which comes under 9,200 megawatts. So we are predominant leader of wind energy. And Gujarat also is the having a more installed capacity. But because Tamil Nadu and Gujarat, yeah, it is a peninsula. It's bounded by 3 sides of water. So naturally, you have the wind speed. Wind speed is one of the main parameter, and wind power density is the main parameter. So for the output of wind power, so this is abundantly we are getting in Gujarat and in Tamil Nadu. And the Tamil Nadu scenario is different because we have the seashores. That is one part. Another one is the Western Ghats. That is the, we are blessed by the abundance of power. So Tamil Nadu is blessed by the abundance of power. So you can see that. So benefits of wind power, you know that it's a clean energy and a safe production of electricity, causes no pollution, the fastest growing and the largest renewable energy sources, and environmentally friendly and sustainable. The technology is not too complex and freely available. So freely available, and wind farm can be easily built. Um, next, state-wise distribution of wind energy in India. You can see the map. See here in the right-hand side, you can see the wind power density. So I said that for any wind potential, wind speed and wind power density is the important parameters. So vital parameters, these two things. So that means the wind power density is showing in this right side. See this, the orange color, which is very 200 to 250. So this comes under in class 1 actually. The wind power classification is classified like that. It is class 1. So it is poor normally. But when you go for a blue and red and green, so wind power density is high. And that green you can see in the map, Tamil Nadu, particularly in the southern tip of India, you have that green color, which means that high intensity, high wind power density is in Tamil Nadu state. So that's what I said is we are Tamil Nadu is blessed by abundant of wind power. How this is happening is because of this 4 passes in Tamil Nadu, wind passes. What we call this is wind passes. Shengota Pass, so which comes under Tirunelveli and Tuticorin, Aralvaimozhi Pass, Kanyakumari, Radhapuram, Muppandal, Kambam and Theni, and Palakkad is Coimbatore and Dindigul. So we have naturally we have 4 passes. So what is this wind passes? The wind passes does nothing but like a gap. Everybody knows that the Palakkad gap. So Palakkad gap only we know, but we have 4 gaps. That's what the Shengota, Aralmari, Kambam. So not only Palakkad. So we have another 4 passes. One more pass is also there, Seashore Pass. That is in Ramnad actually. In this 4 passes, the tunneling effect, like a tunneling effect means like a funnel-like structure. The wind comes and expands the wind, so that we are getting a 18 to 22 kilometer per hour. So every normally we will get. So the wind season for Tamil Nadu is May to September. So this is this season is good actually. So we are getting normally if you see in our state and all 3,000 megawatt normally it will go in this time and all. So 2,000, 3,000. So this May to September we are mainly dependent on this wind energy. So these 4 passes plays a vital role in production of the wind energy. So we have the 4 passes, Shengota, Aralvaimozhi, Kambam, and Palakkad passes. So you can see that. Next. So you can see these 4 passes, Shengota, Aralvaimozhi, Kambam, and Palakkad. So these 4 passes are here. So through these passes, we are getting the normal wind speed. So if you take in meter per second, it comes around 7 to 8, so which is moderate, and 18 to 22 kilometer per hour. So this is the normal speed. So that is possible to produce more output power of wind energy. Next. So site selection. So this is called as a micro sitting, which means how we are placing the wind turbine in the onshore. So onshore means in the plains. So how we are placing the wind turbine. So the distance between one turbine to another turbine in a horizontal distance, it is 5D, the 5 of D, the Habai, the dia. So and 7D is the vertical thing. So you can see in the picture. So area required per wind turbine is approximately 5 acres of land is required for a wind turbine. Next. So far what we have seen is the onshore wind energy. So onshore wind energy is a different scenario. We already proved that in India, we have a capacity, I said 8,500 megawatts. So this is a different scenario. What about offshore is in the sea? In the sea, this wind turbine in European countries, this offshore is a successful project and producing highest more power in offshore. And Tamil Nadu, the project is going to start. So India has around 7,600 kilometers of coastal line. So we have a huge potential of offshore. So offshore in the sense, inside the sea, we have we can see that wind turbine inside the sea. So the ministry has also framed a target for offshore also, medium term 5 gigawatt by 2022 and the long term of 30 gigawatt by 2030. So this is the offshore target of wind power. So this is the offshore target. So this is particularly we are focusing on to this because when you go for a offshore, the capacity is more. Now we have started the project in India. We began the project in 1980s actually. The onshore initially we started 1980. So from 22 kilowatt of wind power. So still 22, 55, and then moved on to 100 like that. Now it is around 2.5 megawatt onshore wind, which means that that is called as the old missions are called as a stall regulated mission, stall regulated. And now today it's a pitch regulated mission. So pitch regulated will adjust the fins, the blade which will adjust, and according to that the speed it'll take you will get a maximum wind power, output power in a pitch regulated. Now there is no stall regulated missions, and particularly all the machines installed here it is LVRT compliant. So everything is a LVRT, low voltage right through. So that means even if you have a dip, the sudden dip or sudden fluctuations or flickers occurring, so the grid should not separate out. We are talking about 1 megawatt or 2 megawatt, a small thing. But if you take in a thermal power station, if suppose the dip occurs or any fluctuation occurs, they have to maintain the grid. So it should not separate out. So that is a big capacity. The conventional power, if you take a 210 megawatt or 600 megawatt, that is a different scenario. But in case of a wind turbine, because every time you have the shift operators will be there in a thermal power station, so they are keep on watching in the SCADA, so they can easily control and monitor and control this. But in case of wind is concerned, it's a farm. It's a farm. So you have a plenty of wind turbine generators around. So every time we cannot watch that one. So it should be provided with LVRT. So that means when you have 100% or 80% it's running, sudden dip occurs means it will withstand without any grid separation. It will maintain the stability. So up to 15%. So now we have all the wind turbine generators are LVRT and pitch regulated machines. So that is the thing. And offshore is concerned, why I'm talking about this one is, this is offshore. We have started from 22 kilowatt, 55, and now 2.5 plus, 2.5 megawatt plus. This is onshore study. And when we are talking about offshore, which comes under 10 megawatt. So imagine that one machine itself 10 megawatt, 8 megawatt, 10 megawatt like that. So that is a different one. So if you add up to the capacity will increase enormously. So this project is going to start up. That's what I said. We have a lot of opportunities. Still, we no need to go anywhere, Germany or France or Spain, not like that. People are even coming from Spain and Germany and all to visit this, the topmost of Tamil Nadu, the Muppandal area. How the pass? What is the pass? What do you mean by pass? This is the Western Ghats. So we are getting a gap. In this gap, we are getting this much of wind power. People are coming from there to see, to visit the Kanyakumari district from European countries. How the structure of, how the topology of Tamil Nadu. So it's a remarkable one. So that means that's what. So we are next. We are moving on to the offshore projects. Offshore is Tamil Nadu again. It's a huge potential we are having. Tamil Nadu is having a huge potential of offshore also. We have a huge potential in Tamil Nadu, onshore, offshore, solar, everywhere we have a huge potential. So this is one thing. And you can see this offshore wind power development. So two states in India, one is Gujarat, another one is Tamil Nadu. So Gujarat is the Gulf of Kampat, this is Tamil Nadu's Gulf of Mannar. So the location is Jaffarbad in Gujarat, and here it is Dhanushkodi. You can see this figure. So you can see that the left-hand side, you can see this Metmast, the top tower you are having now. So that is Metmast. And in the Gujarat itself, you can see that right side is LIDAR. So Metmast here in Tamil Nadu, we have around 100 plus 100 Metmast around. So this Metmast measures this is a Metmast meteorological mast. So this Metmast at various heights from 20-meter hub height or a 50-meter hub height or 100-meter hub height, 75, like the different hub heights are there. So this Metmast measures the wind speed with the meteorological department, the wind speed as well as what is the output power also. So this is mainly for a forecasting of wind power, mainly for forecasting, because today the day ahead schedule we can give, but what is the intraday? Intraday means on the particular day. So that Metmast plays a vital role in onshore. But when you go for offshore LIDAR, so you can this Metmast and all, it won't stand. It is very not that much of strength actually. So LIDAR is a light detection ranging. You know that. So this is the LIDAR placed in Gujarat. You can see that figure. That is the LIDAR. So LIDAR is already placed in Gujarat in 2017. Tamil Nadu is yet to, the project has started, but it's going on due to the MOEF clearance, that is environment clearance. So these clearance and also, once it's ready, in Tamil Nadu, we have a very big project of offshore wind power development, particularly in Dhanushkodi, Rameshwaram. And not only Dhanushkodi, Manapadu, that is in Thuthukudi and Rameshwaram area. So 3 more LIDARs going to place. So initially at Dhanushkodi is the first one. So that is the project is going on. So next. So advantage is offshore. So I said is higher generation. That means when you go for a onshore, I said from 22 kilowatt to we moved on to 2.5 megawatt. That's what initially the project started in Tamil Nadu and Maharashtra, Gujarat only. And we have a good potential. So 2.5 megawatt. But now, if you take an offshore project, 8 megawatt, 10 megawatt, one single machine. So imagine that if you take 100 machines, so 100 into 10, it costs over 100 megawatt, 1000 megawatt. So that is higher generation. Surfaces of the sea are smooth because in a wind there's more turbulence. But in case of offshore, you won't get that much turbulence. So the turbulence is less, and obviously high wind power density when compared to the plains. Offshore is a high wind power density, wind density, and capacity utilization factor is high, and obviously the energy yield will be high, right? So when you have a capacity utilization factor is high, means obviously the yield will be high, and less noise when compared to the land-based turbines. Land availability issues are obviated. So that means in a plane, you have to, that micro thing I said, no, so 5D and 7D. So that much of issues not there. Only in planes, you have a problem with the land, all those things. But in sea, you have a plenty of area. So in the plenty of area, but there also you have to follow the micro setting. So micro sitting is a very important between the clearance between one turbine to another turbine. Simply in a simple word, that is called as micro sitting. So these are all the advantages of offshore wind energy. Next. So you can see this. This is a meso map, a micro map, meso map like this. See in this meso map, this red, you can see that Tamil Nadu, red intensity. So high intensity means high wind potential in offshore. We have a high wind potential offshore in Tamil Nadu. So of the state, you can see the red indication is the highest intensity when compared to the green. So which means that you have a huge offshore wind potential in Tamil Nadu. We have. So this is one thing. And next. So 8 zones are identified in Tamil Nadu and Gujarat actually. So this 8 zones, I said no. So in here, the Gulf of Mannar, in this Gulf of Mannar, Dhanushkoti is the area where the LEDA goes going to place, where we have a huge potential of wind power of offshore. Next. This is the Dhanushkoti area. It's like a what do you call, like a dolphin nose. That means how we are seeing in the Park Strait, that tip you can see in this Dhanushkoti, that nose will be there. Actually, the importance of this particular area is you have onshore, offshore, and seashore. So what a seashore is? This Dhanushkoti, that point indicating no, that is not actually a offshore. It is seashore. It is not neither on onshore or offshore. It is seashore. So this seashore, you can see the metmass. So this figure you can see the next figure in the next figure. The next slide. You can see this next slide. So this is the area surrounded by both the sides of water. You have the tip of the Indian in peninsula. So actually, this is the tip of Tamil Nadu. We can say the tip of the Tamil Nadu is Kanyakumari. So that is one thing. And actually, the tip you can physically, how we are seeing in the map, that you can see in physical. So that nose will be there. So this is the dolphin nose, like a dolphin nose. You can see that seashore is there. This is Dhanushkoti. So here you have a metmass is already placed over there, and LIDAR is going to place for a offshore project. So LIDAR, which will measure what is the speed and what is the intensity, power density, all those things will be measured. So LIDAR plays a vital role. Next. So this is LIDAR. Next. This is the substructure installed in Gujarat, the Gulf of Kambat. I said, so Jafradabad coast. In the Jafradabad coast, this LIDAR is installed. So you can see that in the figure. So this is the same thing is going to install in Tamil Nadu. So that's what I said. The project is going on. So in Gujarat, installed in 2017 itself. Next. Another LIDAR installation. Next. Okay. So opportunities in the sense, already that's what in Tamil Nadu or Gujarat, we have a good wind energy potential as well as wind power projects. A lot of investors, Gamesha, Suzlon, Vestas, Region. So many investors, they have invested, Enercon. So they have invested here in Tamil Nadu. So that's what first is Tamil Nadu is the highest wind power producer. Next to Tamil Nadu is Gujarat. Now in when you go for an offshore, it's another different scenario. So it's a you have more opportunity, employment opportunities more when you go for a offshore wind power projects. It's a different one. So very soon we are going to get these kind of opportunities in Tamil Nadu itself. Nowhere to go. So in Tamil Nadu itself, we have a very good opportunities. Actually, the project is going on. And disadvantages. So disadvantages, as you know, it is not a firm power, it is an infirm power. So available from May to September. And but RLI Mori Pass is different case. In RLI Mori Pass, even after September also, the 2 months gap, from November to April also, it will give a power. You can get a wind power in RLI. So almost throughout the year in RLI Modi, that is Kanyakumari, we will get this much of power. And extremely difficult grid management due to high variation of wind power generation. So that is the grid management is difficult. That's what because as I said, Tamil Nadu is the major producer of wind energy. So if you see 2000 megawatt or 3000 megawatt at this time around, so in this time, so 2000 megawatt if around, suddenly if it is not there, so megawatt is reduced from, say for example, some 100 megawatt. So that grid management is difficult. So we have different source of power. Thermal, gas turbine is, that's called as a spinning reserve, gas turbine, thermal power station, and hydropower. So we will manage the grid management with the help of a spinning reserve. So that is even if we have a disadvantages of in power also, that will be managed by spinning reserve. And a huge investment required for the transmission of RE energy. Next. And when you're talking about wind turbine alone, so not only wind turbine you have work, so we have the tapping of renewable energy. So today, the green energy corridor. So green energy corridor is 7 rich renewable energy states in India, starting from Tamil Nadu, Karnataka, Andhra Pradesh, Maharashtra, Gujarat, Madhya Pradesh, and Rajasthan. These 7 states are rich renewable energy states in India. So the REMC, the Renewable Energy Management Center, it's a part of LD Center, Load Dispatch Center. So in this 7 rich renewable energy states, so they will monitor the infirm power alone. So only exclusively for the wind power. So solar and the wind. So what is the forecasting and scheduling that will be monitored by REMC. So that means we have a this opportunities in operation and maintenance. So you can see this. So how the typical wind farm. So you can see this RE generator. So here the generation voltage is 690 volts. Nowadays we are getting 690 volts. Previously the old mission and all 440 like that. So that is older one. But now the terminal voltage, that is generation voltage is 690 volts. This 690 volts is step up to 11 kV. Next slide. Next. Now, this RE generator, RE generation or developer. So you have a wind farm. So it is classified into 3 verticals. One is RE generator, intrastate, and interstate. So what is this RE generator? RE generator, we have that is the wind farm. So more than 10 megawatt is called as a wind farm. So single generator, so 2.5. If you take that 2.5 megawatt as a single generator, 2 megawatt or 2.5 is a single generator. So when you have more than 10 megawatt, it's just normally called as a wind farm. So normally this investors, I said, no, Region, Gamesha, or they're having their own wind farm. So the substation itself called as a pure wind farm substation, 10-1 substation. They are maintaining the operation and maintenance done by the developer itself. So that is RE developers. So uh, this 690 volts is converted to 33 kV. So 33 kV, then to 110 or 230 kV, then intrastate. So intrastatus, you can see this intrastatus inside within the Tamil Nadu, and interstatus other states. That is the national grid. And electrical systems in wind turbine. So this is called as a substation. This normal substation, and this is pooling substation. This pooling substation means where the wind turbines are connected to the next voltage level. So that is called as a pooling substation. The normal substation you can see in the distribution substation. So that is normal. This is pooling substation. In some cases, in the distribution substation also, you have a dedicated feeder. This wind turbine are connected to the dedicated feeders. So that is mixed feeder. We call as a mixed feeder. This substation is a pooling substation. And you can see here, we have a wide opportunities in these cases. Here we have a wide opportunities. And I said earlier, Renewable Energy Management Center. So we have 7 rich renewable energy states in India. These 7 rich renewable centers, which exclusively for monitoring, that means the forecasting and scheduling of the renewable energy. So this is the functionalities of REMC. So scheduling and forecasting. So next. So this is substation and pooling substation. So REMC, Renewable Energy Management Center. Next. So you have 7 rich renewable energy states. So this 7 rich renewable energy states I said earlier. So this is forecasting and scheduling. Next. Next. Okay, next. AMR. So AMR is automatic meter reading. So for all the wind turbine generators and solar generators also, we have installed the meter, smart meter, for the generators, not for the. Normally we will talking about the smart meter for consumers, not like that. This is for a renewable energy generators. So this renewable energy generators, you can see this. Next slide. Next. Prolonged leak detection, tamper detection. So no need to involve a person there. Okay. So these problems resolving the billing issue, we are getting because the initial reading and final reading and all, we have to go and take the reading. So that and all, it should be avoided in case of this automatic meter reading. Next. So this GSM based, what we are adopted is GSM based SIM. So you can see this. This is the meter. That is, the meter is installed in the premises of a wind turbine generator. With that, you have a meter interfacing unit, GPRS SIM. Through this, the modem will give the signal and connect it to the MDAS, meter data acquisition system. That is the software. That is the database. Next. And green energy jobs. So that's what a lot of opportunities. How these opportunities and all I have said already. And 2 things I have to point out over here. Surya Mitra skills. There are a lot of programs are there. Skill India programs are there. But Surya Mitra skills, it's a free of cost actually. This program is for the IT students and for the diploma engineers. So this program organized by the NISC, National Institute of Solar Energy. Then next. And this is Vayu Mitra course. So Vayu Mitra Foundation, this is wind energy. So Surya Mitra for solar and Vayu Mitra for wind energy. So you can see starting from the wind resource assessment, what all the O&M operation maintenance of wind, everything you can, in this course, they are explaining. Anyway, National Institute of Wind Energy. So they are giving for graduate engineers this course, training for this courses. And one more university in Tamil Nadu, Dindikkal, Gandhigram University. So the Gandhigram University is for IT students and diploma students. They are giving training for this. And one thing I want to add up this point is tomorrow is the last day, 10th. You can see this Vayumitra, and in a Nive website, you can see that Vayumitra course, you can apply for this. They will give a training for entire thing. So tomorrow is the last day, 10th of June. You can Google it and find out this kind of things. So you can make a point of it. This is very even that is from ITA to engineering graduates. This Vayumitra course is available. And thank you. Any other questions, please?
Hello, sir.
Yeah.
So we have two interesting
Hello, sir.
questions.
Yeah, tell.
Yeah, we have two interesting questions from
Yeah,
the
yeah.
participants. One is
Yes, sir,
you are saying that the wind energies, that most of them are installed near to the sea. So you showed some image of Dhanushkodi, right? So
Yeah.
what are all the safety factors that is being considered to protect the wind farms from the cyclones?
Yes, sir. Very good question. Actually, wind power curve. It's a very good question because the investors, they are investing crores and crores of rupees here, right? If you see the power curve, the wind power curve itself, 3.5 meter per second is the cut-in speed. 3.5 or 3. Nowadays, even 2.5 also is a cut-in speed. Cut-in speed means in that speed only the power will generate slowly, and it will reach around some 10 meter per second or 14 meter per second, means it is a rated power. We'll call as a rated power. And 25 meter per second is the cutout speed. This is called a cutout speed. That means this speed, the wind itself is classified into different forms: breeze, gale, storm. You got it? That is, breeze means it's a small. That is a very breezing of air. The breeze, gale, and a storm. Storm is 25 meter per second, means cut out. So the machine itself will automatically cut out because there is no one is there. That's what I said. If you go and see in thermal power station, the operators will be there, the SCADA will operate, that and all is okay. But in a wind farm, no one will be there. So one person will be engaged. But see that one turbine to another turbine itself, the distance between one turbine to another turbine is 1 kilometer. So imagine that you have hundreds of wind turbines. So everyone you cannot monitor. However, we have a SCADA for some system, but 25 meter per second, it's a cutout speed. Automatically, it will cut out. So when it reaches that speed, automatically it will cut out.
So
Then,
yes, sir. Yes, sir. I have
okay.
one more, sir.
Well, yeah, sure, please.
This is from it's a response that we are getting good response from across the Indian country itself. He's from Andhra. His question is,
Okay, thank you.
so based on the investment and efficiency, what is your opinion whether wind is best or solar is best?
That's what I said, sir. So the history began from 1980. We started, the government of India started from 22 kilowatt, I said. So now it's onshore is 2.5. This story is different, but now only that the solar is, that's what, when 100 gigawatt in the sense, 40 for rooftop, and 60 for solar parks. The government itself, solar parks, lot of opportunities. If you want to say honestly, means more number of opportunities in solar only, sir. Because solar, even skilled person, no need. 10th, the qualification is not required that much. That's what I'm pointing out. The solar, even 10th qualification is more enough. So they are doing very best actually. When compared to southern India, northern India, they north part of India, they are doing excellent. Lot of opportunities are there in solar. So now we have added up around the capacity is 4,000 megawatt. Suddenly we have increased in Tamil Nadu. So 1 year back and all, it is 2,500 only. In 1 year, one or 2 years, it has increased to nearly 1,500. Means it's a huge variation. It's very good actually. So opportunities both, sir. Yeah, that's what in onshore, you know, what is the onshore? Offshore project, we have to see that. That means more opportunities are available in Tamil Nadu throughout. So no need to go anywhere. I mean that no need to go outside of that. Tamil Nadu itself is a hub of wind producer. We are the wind producer. So that's what I said.
Thank
Yes,
you,
sir.
sir. Thank you. Thank you for the feedback.
Thank you very much, sir. We gained more knowledge about wind energy and opportunities based on the wind energies. As you said, Indian government upscale the target of renewable energy projects as 175 gigawatts by 2020. Out of this 175 gigawatts, 60 gigawatts is from wind energy. So we hope our students and budding engineers will get more opportunity in this power generation. And also you mentioned that Tamil Nadu is a predominant leader in wind energy. So we hope that we will get and also for budding engineers. And also from your speech, we gained more information about the difference between onshore and offshore systems and also the advantages of offshore systems. That are advantages like a higher generation, high capacity utilization factors, less noise, and land availability. So we hope that the future will be led by this offshore generations, and not only opportunities in the generation side, and also we gain the knowledge that we are having more opportunities in the operation as well as in the maintenance side also. Since this renewable energy generation form has RE generators, intrastate, and as well as ISTS. So I think so we are having more opportunities in this wind energy generation. As you mentioned, this connectivity is based on GSM. So we will have opportunity for the communication engineers also. So the communication engineers can work on this GSM in interlinking these things and the auto meters. And at last, you mentioned about this Sangamitra and Surya Mitra and Vayu Mitra. We hope we will insist our students to register all those things. As you said, I make to remind the participants that tomorrow is the last date for Vayu Mitra Foundation Scare. So I request the participants, the faculty members of various institutes to initiate their students and some of their friends, those who are doing ITA and diploma, to register in it. Thank you, sir. Your speech gave us a very informative thing to us and opportunities in the wind power generation. Thank you very much, sir.
Thank you.
Now it's over to Rama Prabha ma'am for giving introduction about the 5 days of FDP.
Yeah, good morning to one and all, and warm welcome one and all on behalf of Panimalar Institute of Technology and IGEN. And this is the 5 days FDP program. Balakumar sir, he has given a very good lecture about the opportunities in renewable energies. I thank you, sir. Thank you very much. And for the audience, next, it's over to Lavanya ma'am to introduce about the next speaker.
Thank you, ma'am. Thank you very much. A very pleasant good morning. Next, I am very privileged in introducing our next speaker, Engineer C.R. Amuda madam. She has completed her BE degree in Electrical Electronics Engineering at Panimalar University in the year 2011. She completed her PGs at Anna University in the year 2015, both UG and PG with first class in distinctions. She has joined Power Projects in the year 2011 as Power System Engineer, and she was promoted as a Principal Engineer in the year 2016. At present, she is the Manager of Design and Engineering, leading to a team of 15 members. She has a vast experience in load flow studies, reactive power compensation studies, short circuit and transient studies, motor acceleration studies, etc. She is an expert in training power system softwares like ETAP, EC Power, DigiSilent, Power Factory, Power World, PVFit, Dialex, Homer, PSEE, etc. Ma'am, we welcome you to throw lights on the industrial view of wind energy and share your valuable ideas. Ma'am, please, it's your session now.
Yes, Amsamam.
Thank
Yeah.
you, ma'am.
Yeah.
Yeah, thank you, ma'am, for the introduction. I'll start sharing my screen. Hope my screen is visible.
Yeah. Yes, ma'am.
Okay. Good morning, everyone. So I would like to start this industrial perspective of wind energy. So previously, Balaguru sir have given you an idea about the employment perspective. So now I'm going to start with the industry perspective. So followed by the academic perspective. So before going to the session, let me be sure that my voice is audible and about the network stability. Is my voice clear and audible?
Yes, ma'am. Your voice is clear. You can go ahead.
Okay, thank you. So coming to the agenda of the session, so I'm going to cover about the wind energy generation in the across the globe as well as in India. So with that, I'm going to touch some basics of wind energy conversion system. So with that introduction to the basics, so I will move on to the important topic of the syllabus, that is issues of grid connection. So in this entire day, we are going to see about the wind energy system. So in that, the issues of grid integration is going to be the most important topic, and I would like to share some industry point of view in the issues of grid connection. So this is about the agenda of this session. So coming to the global installed capacity of wind energy. So this is the data I have taken from this website. You can see the reference. So from the year 2015 to 2019, you can see the gradual increase in wind energy generation across the world. And the grand total of installed capacity is about 6,50,758 megawatt. It's in megawatt. That is at the end of 2019. So this is about the installed capacity of wind energy across the world. So you can see across the world, it has been increased from the year 2015 to 2019. So in India, I will say in particular in the next slide. So here you can see the growth of wind energy generation in particular, that is from the year of 1981 to 2019. It have very much increased. So you can see this from the graph. So, and you can also see the reference of this. So coming to the installed capacity of wind in India in particular. So this is taken from the CEA website. So I have added the reference here. So this is given for all the generation, that is thermal, nuclear, hydro, and renewable energy sources. So I have taken the renewable energy sources, the breakup of renewable energy sources in detail. So that is for small power, hydro, biopower, solar power. So I'm going to concentrate about this wind power. So it is clear that as on 30/4/2020, the generation of wind power in India, the installed capacity is so 37,745.85 megawatt. So as sir has told in the previous session, it is about 37 gigawatt. So, but there is a decrement in wind generation in the recent days. You can see this data, and I have taken this from the POSOCO site, that is Power System Operation Corporation website. So they have mentioned that in the year of 2019 April, so the wind generation was here, the wind generation is in y-axis, that is it was 3,422 million units. But in April 2020, it was just 2020. It has gradually reduced. In the recent years, we have seen the development of wind energy, but in the last, from compared to the last year, it have decreased to some extent. So this is also taken from the same POSOCO website. So when compared to the other energy generation, that is thermal, this is thermal and this is hydro. So you can see all the generations. So among this, so wind you can see here, it is very decreased. Okay, so this is for the month of 30 April 2020. So recently there is a decrement in the wind generation. So with the statistical data, so I think Balaguru sir have given enough statistical data about the wind generation in India and especially in Tamil Nadu. So with the statistical data, I would like to touch a few basics on wind turbine technology. So from the picture, it's clear that what is onshore wind turbine and offshore wind turbine. So onshore wind turbine is the wind turbines located on lands, and the offshore wind turbine is located on the water bodies, especially ocean. So with this, I would like to post a question to the audience and participants. So do anyone have an idea of which is the largest wind turbine generator in the world? So I repeat the question. So which is the largest wind turbine generator in the world? So you can post your answers in the chat box. So I will give you some 10 seconds and then move on to the next slide. You can verify your answer. Okay, let me
We
tell
have
the
got the
answer.
answer, madam. It's 12 megawatt GE from
Okay.
Maharaj from
Oh, very good, very good. So let others also know the answer in detail. It is correct. That is Haliade X. It is the installed capacity of Haliade X is 12 megawatt, and it is the largest offshore wind turbine generator located in Netherlands, and it is supplying power to Inaco, the Dutch utility. And you can see the specifications of this largest wind turbine generator. The rotor is of 220 meter and the blades are of 107-meter high, and the height of the wind turbine is 260 meters. So, and one more thing, it has set a world record recently by generating 262 megawatt hours in a single day. That is a clean energy in a single day, so which is sufficient to power 30,000 homes. So it is such a most powerful offshore wind turbine. Okay, with this interesting fact, let's move on to the next slide. So I hope all these wind turbine components are familiar to you. So you could have seen all this and you could have studied in this. But let me give a short introduction, very short introduction, because I hope this will be covered in detail in the academic view. But without this, I can't move on to the important topic of issues of grid connection. So let me give a short view on this. So this you know very well. That is, this is your wind blade. You will have a pitch system, you have a brake, you have a yaw motor, and this is nacelle which houses the generator controller, etc. And this is anemometer to measure the speed of the wind, and this is wind vane, and this is a generator. So this is just to give an idea about the wind turbine generator. So, and I'm also sure that you could have heard across, you could have come across all these terms, that is cut-in speed, cut-out speed. That is from the graph, it's clear that cut-in wind speed is a minimum speed above which your generator starts generating. So, and once it reaches the rated wind speed, so the power output will be constant in case of pitch regulated wind turbine, whereas it increases and then decreases in the case of stall regulated. These stall regulated wind turbines are very conventional. So, and coming to the cutout wind speed, it is the maximum wind speed above which your wind turbine should not generate. Otherwise, it will damage your blades, your wind blades, and it will decrease the lifetime of your wind turbines. So there will be a cutout wind speed, which is the maximum wind speed at which your wind turbine generator will generate the electricity. So next, you know about the rotor speed, the speed of the rotor, and tip speed ratio. So the ratio between the rotor speed, that is blade tip speed, and with that of the wind speed is the tip speed ratio. So that determines the efficiency of your wind turbine generator. And these lift force and drag force, you would have studied the aerodynamic principle in detail. So how about the airfoil structure, angle of attack, all these things. Any doubt? Okay. So all this thing you would have studied. So this lift force is primarily responsible for the rotation. I mean, responsible for the dark to rotate your rotor. So that is primarily responsible, this lift force, and this will be perpendicular to the direction of wind. So if the lift force is higher, so the blades will, the efficiency will be high. But if your lift force is lower, if your drag force is higher, the angle of attack will be higher. And if it is stall regulated, the efficiency will be very low because the energy captured by the wind will be suboptimal. It will not be used, it will not be utilized completely. So, but if you go for pitch control, so you can see this in the diagram here. So in the pitch control system will rotate the blades in the direction of wind so that efficiency of the wind turbine will be high. And in an advanced technology of yaw control, your yaw motor will turn the entire rotor blades towards the direction of the wind, and it is an advanced technology, and the efficiency will be very high in yaw control system. And one important question for the participants. So I've given the answer also, but you can just guess why we are not going for 2 blades and why we are not going for 4 blades. Why it is specifically 3 blades? Somewhere you can see, but which is the most efficient one? Either 2 blades or 4 blades or 3 blades. So just put your answer in the chat box. So we will discuss that at the end of the session. Now coming to the most important topic of wind turbine classifications. That is, all of us know mostly that is there are 4 types of wind turbine technologies. That is type 1, which is fixed speed wind turbines, and type 2, which is variable slip wind turbines, which is type 3, doubly fed induction generator wind turbines, and a type 4 full converter wind turbines. So coming to the type 1 fixed speed wind turbines. So it is a squirrel cage induction generator, and it will not be having any specific control system to vary the speed. That's why the name fixed speed. The speed variation will be very less than 1%, that so that we can call it as a fixed speed wind turbine. And the real power compensation is required for this type of turbine, so that we'll be always providing a capacitor bank for this. So let me discuss the effects of these capacitor banks at the end in particular. So, and we'll be having a soft starter, and it is directly connected with the grid. So, but the reliability will be high, and it is usually stall regulated. I have told you stall regulated when I told about the lift force and drag force. So these types of turbines are usually stall regulated. Very rarely it is pitch regulated. So the overall efficiency will be very less. So in recent days, we are not using this much, but they have installed it some few years back, so it is still in operation. So we have to know about this too. So here are some points about the fixed speed wind turbines. So as I told, it requires reactive power, so war compensation is necessary. So coming to the variable speed wind drives, these are slip ring induction generators, where you can have an external resistance. So if you adjust this resistance, your speed will be variable. So we have a variable speed wind turbine, but one disadvantage is that, so when you vary the resistance, the losses will be more because heat will be dissipated. So, and the losses will be there. You can see that for every 1% increase in the slip, you'll be having of 1% losses. So this is a major drawback of this type of wind turbines. You can have a wind variation, that is variation in the speed of 10%, but the losses will be very high. So this is about the variable speed wind turbines. And coming to the doubly fed induction generator, so losses will be very less. It have a back-to-back AC/DC and DC-to-AC converter systems, so that and it is also connected to the grid. So the speed is you can vary the speed gradually, and the losses will be less with such an efficient system. And it is since it is doubly fed, it can take the reactive power from the grid when needed at the starting of the generator, and once if it starts generating, it will supply power to the grid. So it is anyway dually connected. That is why the name doubly fed induction generator. And some points about the doubly fed generator, or the bidirectional power flow will be with us since we are using a converter. Losses will be very less because many of the losses are dissipated across the slip ring in case of type 2 generators. But here the losses are recovered and it is sent to the grid. That is a very important point about the doubly fed induction generator. So moving on to the next type, that is full converter wind turbine. So we'll be using this the same back-to-back converters, but one different thing between the type 3 and type 4 is, and this one is it may be either synchronous generator or induction generator, but one thing is it is not connected directly with the grid. But in the previous type 3, you could have seen it is directly connected with the grid and also through the back-to-back converter. But in type 4, it is connected. The only path of connection between the generator and the grid is the full converter. So it is the path will be through the converter only. This is an important note about the type 4 converter. And it offers independent real and reactive power control. That is a very important thing. So, and as I told, it may be either synchronous or induction generator. So far we have dealt with the statistical data and some basics of wind turbine technology. So now only we are going to touch the important topic of industry perspective session, that is issues of grid connected wind turbines. That is when you're integrating your wind turbines with the grid, power grid. So what are all the issues you are facing and how to overcome it? And what are all the grid code given by Indian grid code requirements? That is all very important when we go for integration of wind farms with grid. Okay. So you can see the picture here, the grid integrated wind turbine is there. So what are all the issues they are facing? That is, what is the short circuit contribution? What will be the harmonic distortion? Flickers will be there, voltage unbalance will be there, voltage drops will be there. So voltage right through complaints should be got, and the active power control should be there, reactive power control should be there. So we are going to discuss all these issues in detail. Just I have listed out the issues. That is, we are going to check the voltage profile, and we have to make a note on the short circuit level and stability. All these are one or the other way related. LVRT complaints, HVRT complaints. How is the real power and frequency response, and how is the power, and how should be the power quality? What is the impact of losses, and how the protection and relay coordination should be? So let's see everything in detail. So, but before going to that, I would like to give the grid code for integration. That is, when you are integrating the wind farms with grid, so you have to be very aware of what is the grid code requirement given by our country. That is, wherever you are locating and wherever we are integrating our wind farms with the grid, so we have to follow that country grid code requirements. So I have listed out our grid code requirements here. So you're gonna have a glance in it, but I'm going to discuss all this in detail. But let's have a short view on this. So our grid should be capable of operating in the frequency of 47.5 hertz to 52 hertz. It should be, your generating unit should be able to operate. That is, it should be able to generate in the frequency range of 47.5 to 52 hertz, but it should be able to deliver its output in the frequency range of 49.5 hertz to 50.5 hertz. Okay, this is the generating frequency, and that is the delivering frequency. And this particular condition is also subjected to a condition. So I will tell that in detail in the upcoming slides. So, and low voltage right through and high voltage right through complaints is mandatory. So I will tell this about, I will tell this in detail. So, and it is sufficient and it is mandatory to maintain the power factor within the limits, that is 0.95 lagging to 0.95 leading. Very important thing. And this depends on the reactive power support needed. So accordingly, a reactive power support should be there. So, and you have to maintain a power factor of 0.5 lagging to 0.95 leading. And the very important thing which denotes the stability of the system is short circuit ratio SCR we used to call usually. So it should not be less than 5. So usually our wind plants and solar plants will be having less short circuit contribution. So I will be dealing this in detail. So let's see that in that particular slide. So that the limits of voltage harmonics and current harmonics should be in accordance with this standard. So this is just an outline. So let's see this each point in detail. So coming to the voltage variation, so you could have seen in this graph, this is nothing but an voltage interruption. This is nothing but a voltage sag. This is an voltage swell. So all these are power quality issues, and not only that, it may be due to any of the faults or whatever problems in the grid. So this all these power quality issues are often common in the grid. Okay, so during that time, what should be the voltage variation allowed? That is the main thing I'm stitching here. So the voltage variation in your grid connected wind farms should be limited up to plus or minus 5% only. Okay, this is very, very important. So, and I will deal with this voltage variation with the short circuit contribution in detail so that you can understand very clearly. So this voltage drop and the short circuit contribution are one or the other way related. So I will tell you in detail in this slide. So the short circuit ratio determines the strength of the system. So when you say if the short circuit ratio is if of a greater value, it is a strong system. So if the short circuit ratio is of lesser value, then it is a weak system. So I will tell you how we are naming it as strong or weak system. So first, short circuit ratio is the ratio of your short circuit current and the load current. Take for example, if you're taking a system of short circuit current 20 kiloamps, okay. So and if the load current is 1 kiloamps, say the short circuit ratio will be 20 by 1. Just for simplicity, I'm taking load current as 1 kiloamps. So it is 20 kiloamps by 1 kiloamps, which is 20. So if your short circuit ratio is 20, so the voltage drop is nothing but 1 by short circuit ratio. So if you take the reciprocal of this, you will get 5%. So this is a strong system. So you can't understand that if I say this is a strong system by saying the details of this system alone. So let me take another system. So let us short circuit ratio be 5. That is short circuit current of the system be 5 kiloamps and let the load current of the system be 1 kiloamps, so that the short circuit ratio will be 5. So what will be the voltage drop? So it will be 20%. That is 1 by 5. It is 20%. So from this voltage drop, you can easily understand or you can easily get the point that whenever if a system have 5% voltage drop or if a system have 20% voltage drop, this will be the strong system and which will be the weak system. So it's undoubtedly the system with 5% will be a strong system and the system with 20% will be the weak system. So we can conclude that SCR ratio with greater value will have a strong will be a strong system and SCR with lesser value will be a weak system. So that's what I'm trying to say. And you can also see the voltage drop variation. I have told that it should be less plus or minus 5% is allowed, which means your short circuit ratio should be high so that your voltage drop should be less and it should not be plus or minus 5. It should not be more than plus or minus 5%. That is the tolerance limit allowed for the voltage variation. Okay, then coming to the short circuit contribution. So if it is 20, our short circuit is 20. So if it is 5 kiloamps, short circuit ratio is 5. So coming to the short circuit current, if you have very less current, so your stability is CR with 5 is a weak system. So the stability will be very less. So FCR with 20 is a strong system. So stability will be more. So this is one or the other way related to the stability of the system also. So we always prefer to have a system with SCR of higher values. So that's why the grid code requirements have stressed a point that SCR, the interconnection point, that is where you are integrating your wind farms with the grid, should be connected, that should be not less than 5. This is what I am trying to stress. So the SCR at the interconnected point should not be less than 5. But usually our wind plants and solar plants will be contributing very less short circuit current. That is why they are stressing the point that it should not be less than 5 kiloamps. And sorry, that is that should not be less than 5. The ratio should not be less than 5. So it depends on your load current as well as your short circuit current. So coming to the very important point of LVRT complaints, that is LVRT is low voltage right through. So low voltage right through complaints is a very important one. So, and we have two things. One is LVRT and another one is HVRT. One is low voltage right through and another one is high voltage right through. So in the name itself, we can get an idea that so the our integrated wind farms with the grid have to ride through this low voltage or high voltage. So I will tell you the exact lines from the grid code requirements. That is, the generating station should be connected to the grid. So, and it should remain connected to the grid when the voltage at the interconnecting point on any or all the phase tips should be depicted by the thick lines. So actually here a thick line is depicted. That is, it shows the variation of voltage from 0.9 per unit to nearly 0.15 per unit. You can see here. So it is 0.15 per unit. So whenever in the grid connected, when the wind turbine integrated grid, so when your voltage dips from 0.9 per unit to 0.15 per unit, during this voltage dip, your wind turbine should be connected, should remain connected. It should remain connected to your grid. Either the fault may be in one phase or all the phases. So till this voltage drop clears, till either it may be due to a fault or whatever may be. So till this fault clears and till this voltage reaches this value, your grid wind farms has to be remain connected. It has to be stay connected with your grid. That is what the main point. That is what the main requirement by Indian Grid Code. So this is the LVRT complaint. So you have to when you're having a wind farm, you have to do LVRT studies. So you have to see the dynamic performance and then you have to get the LVRT complaints. This is highly essential. And during this voltage drip, the reactive power supply is of first priority and the real power supply is of second priority. So the first priority has to be given to the supply of reactive power. Okay. And one more thing is that when the real power is reduced to, and the real power should have to retain its value of 90% of the pre-fault level within 1 second of the restoration of voltage. That is, if your voltage is restored within 1 second, your real power has to be restored to 90% of the pre-fault level. So which was the voltage level during the pre-fault condition. So of that 90% should be restored within 1 minute. That is the grid code recommend. That is also to be noted. So all these comes under the LVRT study. So this is a very, very important thing about very, very important issues and very important study that has to be carried out when we go for integration of wind farms with the grid. So coming to the HVRT compliance, so we have seen LVRT low, that is voltage dip, the name low voltage. So similarly for high voltage right through HVRT, so whenever your grid faces high voltage, so the point of interconnection that is between your wind turbine and that grid, the point of interconnection should remain connected. That is the point they are stressing in HVRT complaints. So this is clearly depicted in the table. I will explain this table. So whenever if the voltage is less than or equal to 1.1 per unit, so that is from 1 per unit is it is say it is increased to 1.1 per unit. So your wind farms has to remain connected continuously to the grid. Okay. So but if the over voltage increases from 1.1 per unit to 1.2 per unit, so your grid has to be remain connected for 2 seconds. So this time it has to be remain connected. This is a minimum time it has to be remain connected with the grid. And if your voltage varies from 1.2 per unit to 1.3 per unit, that is it still goes higher. So it is sufficient to remain connected for 0.2 seconds. 0.2 seconds. Okay. So if the voltage goes further higher, that is if the voltage increases above 1.3 per unit, you can go for instantaneous trip of your wind farms. So this is a very important mandatory condition for HVRT. So your wind turbine has to ride through this high voltage. This is about the HVRT complaints. So, and coming to the most important point, real power frequency response, I already stressed this point of the generating units shall be capable of operating in the frequency range. So the wind farms generating units, the wind generating units, it can capable of operating in the frequency range of 47.5 hertz to 52 hertz, and it can deliver its output in the frequency range of 49.5 hertz to 50.5 hertz. This is a very important thing, but all these are subjected to a condition. So this is what the condition is listed in the table. So I will explain this table in detail. So this has to be satisfied, and this is given in the grid code requirement. So for any wind turbines, sorry. So for any wind turbines of capacity 10 megawatt or higher than that, and operating with the voltage level of 33 kilovolt and higher, so the generating unit should be equipped with the facility to control its active power injection to the grid. Okay, that is, it should control its active power injection at a set point as described by its load dispatch center. Either it may be regional dispatch center or it's a state load dispatch center. So it has to control its frequency, that is, it has to control its active power injection. And not only that, it may have some governors or frequency controllers, and the group characteristics of those frequency controllers or governors should be from 3 to 6% only. The group characteristics should be from 3 to 6% only, and the deadband should not exceed plus or minus 0.03%. This is a very important condition about the frequency control. And a very important thing is that, so whenever there is a frequency variation, and if the frequency deviation exceeds 0.3 hertz, so within 1 second, your generating unit should have the capability to provide an immediate response of real power primary frequency response should be there. Okay, and it should be given within 1 second. So I will stress this point once again. So whenever there is a frequency deviation that exceeds 0.3 hertz, so your generating station should provide an immediate primary real power primary frequency response. So at least for 10% it has to be provided. That is, the response should be of at least 10%, and it should be given within 1 second. That is the main thing. It should be given within 1 second. Okay, so from 10% it may vary up to 100% of its maximum active power capacity, but minimum 10% it have to supply. It has to it should have an immediate response within 1 second. That is another one condition regarding the real time frequency response. And the rate of change of active power should not be more than plus or minus 10%. The rate of change of your active AC active power should not exceed plus or minus 10%. So all these are the conditions regarding your real power frequency response. So all these conditions have to be satisfied. So if it is a generating station of aggregate capacity, so for example, if you're having some 10 wind farms and the aggregate capacity is 500 megawatt, in the sense that type of wind farms, and if you're integrating it with the grid, means for that they can have a provision to receive the signal from the state load dispatch center or regional load dispatch center. So accordingly they can vary their active and reactive power output. So but all these are for installed capacity. This condition is especially for the installed capacity of 10 megawatt and operating voltage range of 33 kV and above. So the installed capacity, the wind farms with the installed capacity of 10 megawatt and higher and operating at a voltage range of 33 kV and higher has to follow all these conditions of real power frequency response. So, and coming to the next power quality issue, one of the famous power quality issue that everyone know. So all these lines were taken directly from the Indian grid code requirements. That is the harmonics we know very well. It is created by the non-linear characteristics of either it is a generating source or load. So it is created by the non-linear characteristics of the system. So if it is a linear one, we will not be having harmonics. So but once if you are integrating your wind farms with the grid, so the voltage harmonics and current harmonic limits have to be checked. So the limits of voltage harmonics and current harmonics have to be checked with reference to the standard IEEE 519 2014. So some may be aware of the standard and some may not have an idea. So I will show you the voltage limits prescribed in this standard. So our Indian grid code requirements is saying that, so with respect to this standard IEEE 519 2014, we have to check our voltage distortion limits and current distortion limits. So just for your understanding, I have given a linear and non-linear load characteristics. So if it is a linear load, so your current will be proportional with respect to your input voltage. That is, your output current will be proportional to your input voltage. Then it is a linear characteristics. So if your output current is not proportional to your input voltage, then it is a non-linear current. So that causes your harmonics. So this is the voltage distortion limits given in IEEE 519 2014. So they are saying that you have to check the bus voltage at PCC. So if it is less than 1 kV, that is for the low voltage distribution systems, usually we will be employing at a range of 4 and 5. So for that and all, so the individual harmonic should not exceed 5% and the total harmonic distortion should not exceed 8%. And hope everyone knows what is individual harmonic and total harmonic. So if you take the square of sum and taking it as a percentage with respect to the fundamental, it is treated as a low total harmonic distortion. But if you're taking a single individual harmonic, either it is a fifth harmonic or a seventh harmonic in particular, and comparing it with respect to the fundamental, it is an individual harmonic. So the limits are prescribed here. So the individual harmonic should not exceed 5 and the total harmonic should not exceed 8. So similarly for different voltage ranges from 1 kV to 69 kV, 69 kV to 161, similarly for up to all the voltages, that is voltages higher than 161 kV. So the individual harmonic limits and the total harmonic distortion limits are given. And there is an exclusion when you go for a HVDC terminal, instead of 1.5, 2% is also allowed. This is what is note. So this is about the voltage distortion limit. So once if you are going to integrate your wind farms with the grid, you have to be very careful about the voltage distortion limits. And one important thing is that it is to be seen at the point of common coupling. So you no need to check the harmonic at all the points. So it is sufficient to check the THD limit at the point of common coupling. That's what IEEE 519 says. So coming to the current distortion limits, so we'll be checking this with the short circuit ratio. I have told you that the ratio of short circuit current to load current determines the strength of the system. So based on that value, we have to check the individual harmonic. So whether it is lying within this particular limit or not. So for this, we have to know the short circuit contribution and load current of the system. So from that, you have to check the range. In particular range, you have to check the corresponding individual harmonic, whether it's lying within the prescribed limit or not. Or you can go for another limit such as TDD, total demand distortion. Actually, THD is a total harmonic distortion, which is compare the individual harmonic with the fundamental one. So TDD compares your individual harmonics with the load current. So that is the difference between THD and TDD. So you can check this also for your when you go for integration of wind turbines. So, and one important thing is that, so if you are checking for either voltage distortion limits or current distortion limits, if your THD is well within the limits, then no need to worry about it. But if your THD varies, then definitely you have to go for either active filter or passive filter or any hybrid filters, or so you have to suppress the harmonics at the point of common coupling. So this has to be taken care. So coming to the impact of wind turbine generators on losses. So it depends on the load and the generation, wind turbine generation. So if your generation is low and the load is light, so no significant losses will be there. And if the generation is low, either it is normal, light or peak load, no significant losses will be there. But if your generation is nominal, but you are giving a very light load, there may be chances of increase in the losses. And if it is a nominal and peak load, losses will be reduced. But this is the important case has to be considered. When you go for a high generation and you are using a light load, means your losses will be very increased. Whereas in the case of normal and peak load, it will be reduced, but this is a case to be considered. So when the wind generation is high and they are using a light load in the sense, so it will increase the losses. So this is also one impact, and you have to check on to this. And one of the main thing, that is the protection required by the Indian grid code is, so all these are the minimum protection required. So your wind farm should have a under voltage or over voltage protection, under voltage or under frequency, over frequency protection should be there. So over current and earth fault protection should be there. Negative sequence protection should be there in case of load unbalance. And the grid connection transformer, it should have differential protection. And in type 1 in wind turbines, you will be having capacitor bank especially. So for that, you should have capacitor bank protection. So all these are the minimum protection required by Indian grid code requirements. So you have to ensure that you are having all these protection systems. So, and finally, I would so I would like to conclude with this. So coming to the industry perspective, I would like to add value to this program by just giving introduction about these softwares, which will be more helpful in studying the dynamic characteristics of wind turbine systems. So I have just listed out a few softwares which will be useful for modeling as well as to evaluate the wind turbine generators. That is, if you take ETAP, you can model for just load flow studies and harmonic studies you can model. So as I told you, the harmonics should be within such prescribed limits of IEEE 519. For that, you can go for ETAP. So there you can model all 4 types of wind turbines. So if you take Dix Island Power Factory, so well you can study the dynamic response of that is LVRT, HVRT studies can be done in Dix Island Power Factory better than ETAP, and ETAP is only for load flow studies, but in Dix Island Power Factory you can do even better. And in Homa, this is not a technical software, this is a commercial software where you can have an idea of what will be the initial cost of your wind farm. That is, before installing your wind farms, you have to use the software of Homa Pro. This is just a commercial software, so which will give you an idea of plant utilization factor, so the initial cost of investment. So everything regarding the cost basis, it will be giving you an idea, the Homa Energy or Homa Pro. So next one is a very important software, PSCAD, that everyone knows. It's a very ultimate software to study the dynamic response of grid integrated wind turbines in all aspects. So this PSCAD will be very useful to study the dynamic characters. So this is all about the introduction of
madam.
softwares. I hope this will. Thank you.
Thank you. I mean,
So
it's a
any
brainstorming.
questions?
It's a brainstorming session because we are talking about renewable energy sources and integrating it with grid. So your session added and value what impact it is going to grid and what impact it is going to create when you add some renewable energy sources to the grid, and what are the things we have to go with. We have to consider with respect to the compliances. What our Indian grid code says, what are the compliances mandatory. So we have an interesting question from the participants. The people all are stressing with the LVRT and HVRT studies. And his question is why the harmonic study is important? In what way it is going to affect? Why it is important? Apart from HVRT and LVRT, we have to add some value, right? So why harmonics is important with respect to this wind generation units? Why it is important for grid connection?
Okay, a very good question. So actually, many of us, not only him, so many of us will be considering about the LVRT and HVRT studies only, but many of us will not be caring about the harmonics. But it is a very important point given in the grid code requirements. That why? Because sometimes if you're in your wind farms, that is, if you're using just take type 1 wind turbines. So as already I told you, it needs reactive power compensation. Okay. So for that, you will be using capacitors. So you could, if you use capacitors, so there may be some chance of resonance. So it will increase your harmonics. This I could see. I mean, with the help of ETAP, you could have seen this better. But just try to evaluate. So whenever you are using capacitors, so there will be a chance of resonance, and
sorry.
it will definitely increase your TH.
Sorry, madam. Sorry to interrupt because other
Yes,
speakers
sir.
also waiting. Yeah, very quickly to answer that question, I think
Okay,
means
okay, I will
say,
conclude. Okay.
Yes, madam. Quickly, let me answer that question and I'll conclude. So, thanks,
Okay.
Amata madam, for
Okay,
your
okay.
wonderful session. So, to question about harmonics, means as long as the power electronic converter is there, harmonic is important. And means your type 3 and type 4 wind turbine generators are of power electronic based converters. So, that have harmonics, and for that, you need to perform a harmonic study. That is a very quick and simple, short and sweet answer.
Yes.
And
Yes.
thanks, Samudha madam, for
Yes,
your
that's
wonderful.
what I'm trying to say.
Yeah,
The next
yeah,
thing.
perfect.
Okay.
So thanks
Thank
a
you.
lot,
Thank
madam,
you.
because other
Thank
speakers
you.
are waiting and we are running short of time. Yeah, thanks
Thank you.
for
Thank
your
you. No,
input. Yes, madam.
thank you. Thank you, sir.
Yes, madam. Now I invite madam to introduce the next speaker.
Yes, sir. Our next speaker is Dr. Umashankar Subramaniam, sir. He is working as an associate professor in Renewable Energy Research Lab, College of Engineering, Prince Sultan University, Riyadh, Saudi Arabia. He co-established the Renewable Energy Lab and directed towards the renewable energy and EV related research and projects as per 2030 vision of Saudi Arabia. He is a guest and special editor of high impact journals and prestigious conferences. He received Danfoss Innovator Award, Mentor during 2014-15 and Research Award from VIT University during 2013-18. He also received the INAE Summer Research Fellowship Award for the year 2014. Sir, we are eagerly waiting for your academic view in Unit 2, that is our wind energy system. Sir, the session is yours. Please welcome, sir.
Thank you so much. And
Yeah, Umashankar sir, probably you can switch on your video. So because people, those who are watching, means may not be able to see your face. So at least for a first, before going for a slides, you can at least show your video. Then probably you can go to slides.
Sure. So very good morning to one and all present here. And I think I enabled the video now. Yeah. So thanks for this wonderful invitation for sharing my research aspects as well as some theoretical aspects. Okay. And as far as my understanding, most of the theoretical aspects are covered in the previous sessions. So mostly I'm going to touch the various research possibilities in the wind energy scenario, and what is really happening in around the world, as well as what is happening in India. Okay, especially. So I'm going to cover only in this aspect, and so let me share the presentation now. So are you able to see this?
Yes, sir. It's coming up. It's coming.
Okay.
Yes, sir. Perfect. Good to go, sir.
So you are able to see the full screen now?
Yes, sir. Yes, sir.
Okay. So wind energy systems, it's not new to India actually. It has been started in the year 1980s onwards, and it has been going on till now. And many of the wind turbine or wind farm installation, if you go and see in, for example, in Palladam or in Kayathar or Nagarkovil, okay. So most of the places you can even look at the old wind turbines which is installed by Danish people, okay, and tie up with Indian government. So we are not new to the wind energy, and in fact we are pioneer in wind energy and wind turbines, as well as we have a lot of R&D industries as well as the manufacturing industries in India. Okay, and one of the famous company called Switzerland, which is also having a lot of plants here, and most of our Indian generation, if you look at, so we are depending on wind. Okay, so now only as for the government's initiative, so we are moving to the solar. So why the wind turbine or solar is very important? Because it's a clean energy. So that's one important thing. So we were depending on only the thermal right? And now we are slowly moving towards the clean energy generation or the wind energy generation. Okay, so wind power, if you look at for the last 10 years, it has been in a very good growth, especially because of the government's initiative, National Institute of Wind Energy and wind turbine research station, okay, which is in Qatar. So they are doing a lot of support for the Ministry of New and Renewable Energy. And now you can see that in the near future, you can see the offshore wind turbines. Status of India, if you look at, we are in number 4. So behind us, you can see that China is number 1 and United States and Germany. And if you look at the installed capacity, we reached around 37 gigawatt, and which is not, we are not completely fulfilled the potential. Okay, so our full potential is 300 gigawatt. So it's almost, we need to go 10 times more. Okay. Added capacity wise, if you look at this time, it's a little bit slow because of the coronavirus in 2020 in the Q1. But in 2019, if you look at the worldwide wind power capacity addition, it is around 650 gigawatt. About 59 gigawatt added in 2019 alone. Okay, so total is coming around 650 gigawatt. So in this, if you look at the contribution from Asia, it's much more, and Europe is next, then North America, then Latin America. So it really shows a very good scope, as well as the near future. The Asian region is going to play a very good role in this wind energy. Comparing the specification wise, and I think the earlier session they already clarified. So what is the biggest wind turbine, which is in Netherlands by the General Electric, and in India we have various kinds, like starting from 1985 to now. If you look at, so we have various different capacity, but still we can reach that level. Maybe the one reason is in India we have not picked up offshore wind turbines. Okay, so but in abroad and all, the onshore wind turbine is almost saturated, and they are moving to the offshore now. Okay, offshore also in some countries it is almost saturated. Okay, so this is the scenario. But in India we have a very good potential in onshore as well as offshore, future offshore. So GDP is also one important thing where you can find that. So whichever country is having a very good GDP, so they have a very good plan for this investment in the renewable energy sector, especially the wind. Okay, so China, you can see they are having a very good GDP, as well as they are number 1 in the wind turbine installation. Similarly, US as well as Europe. Okay, so this is also playing a very good role, especially the GDP. The wind power installed capacity in India state-wise, if you look at, Tamil Nadu is having a major portion, which is having almost 9,000 megawatt. Okay, at the end of October 2019, and followed by Gujarat, Maharashtra, Karnataka, and so on. Okay, the total, if you look at, it is coming around 37 gigawatts. Okay, or 37,000 megawatt. And when you look at the quarters in 2019 and up to 2020, okay, so there is a pickup in the 2019, but there is a marginal slowdown in the third and fourth quarter of the 2019, and even in the first quarter of 2020, it is much lower because of the corona issue. Okay, and the below graph is showing the cumulative wind power installations by the state. Okay, so Tamil Nadu, Gujarat, and Maharashtra, like that. And the reason is the majority has been added in the Tamil Nadu. It's about 25% is added. Okay, so before going to that research aspect, so I would like to show something like wind basics, and how the wind is produced, and how the wind is rotating the blades, how the rotation of the blades converted to electrical energy, and how does a wind turbine work. So for all this, so nowadays you no need to explain through the books. And now everything is available in the internet as animated resources. So for this, first of all, I'd like to say all of you know about the physics. Okay, so the physics is nothing but which is teaching kinetic energy. Okay, so the kinetic energy is one of the important point where the wind is carrying this kinetic energy. So this kinetic energy, which is hitting the blades and which is converted to mechanical energy, as the reason for the rotor is rotating, so it is converted to the mechanical energy, and which is carried over to the shaft. So the shaft is connected to the generator, okay, electrical generator. So this generator is rotating because of this mechanical energy, and which is converted to electrical energy. So there are a lot of energy conversion. So it is something like energy conservation law. Okay, so neither energy is neither created nor destroyed, right? So that's the reason. So one form of energy is converted to another form in this. Okay, from kinetic to mechanical and mechanical to electrical energy. So many of you might have seen different parts of the wind turbine so already. So I would like to show you again. Okay, so the inflow of wind which is hitting the blades. So the blade is rotating. Okay, and now if you look at so the blade is rotating like this, and because of that, the shaft C is rotating. So the C is connected to the D. Sometimes it is a gearbox, okay, which is needed to match the speed of the generator, okay, because the blades may rotate at the low speed and generator may rotate at the very high speed. So in order to match the speed, you need to use the gearing mechanism, okay. So this gearing mechanism, again, it is connected to the generator. And finally, from the generator, the electrical output is taken out through the cable, and which has been connected to the underground substation. Okay, so this is what the fundamentals of the wind energy conversion. So how the electrical energy is converted. Okay, so how the wind is produced. Okay, this is a very important thing. So maybe you can just have a look at it. Okay, so normally, so people from Chennai, you might be knowing very well, right? When you go to the beach, so how you are getting the wind, comparing to the one if you are in the home. Okay, so the obstacles are very, very speed breaks for the wind. Okay. So how the wind is rotating the blades, so already it is explained. It is because of the lift and drag force. So the combination of the lift and drag force only, which is causing the rotor to rotate. So, okay, so both forces is very important, and nevertheless, you cannot avoid any of the forces. Power from the wind, okay, normally the force multiplied by the velocity. So if it is a rotational power, it is a torque. Okay, torque is nothing but the rotational force, right? So rotational force multiplied by the rotational speed is your power. Okay, so if you substitute this equation, so you may get the equation like this: half rho Cp into AV cube. Okay, where you can clearly understand from this. So the power is proportional to air density rho, and Cp is the efficiency coefficient, and A is the gross rotor area, and V is the wind speed. Okay, so in this equation you can understand clearly. So which is the majority? The velocity is the majority, because the power is proportional to the cube of the velocity. So how the velocity, wind velocity, is very important. Okay, so based on this only, we are doing a lot of pre-analysis before installing the wind turbines. We need to do a lot of analysis on sighting, and as well as the data collection, wind speed data collection. Okay, so which is very, very important before installing the wind turbine. Okay, and another thing is the coefficient of power, Cp. Okay, which is also very important, because it is another name for this is the Bates limit. Okay, so the Bates limit is nothing but which is giving the information like 59% of the available wind power only converted to mechanical power. That means the remaining as the losses. Okay, this is what the Bates limit indirectly says. Okay, they can even say that the optimum value for the Bates limit is a 0.593. Okay. And the Cp, if you look at it, is a function of two parameters. One is a pitch angle and tip speed ratio. Why this is important? Because based on this only, you can do a lot of research in the maximum power point tracking. Okay. So by adjusting this pitch angle as well as the tip speed ratio, so you can do a lot of analysis in maximum power point tracking, so which is very useful for the initial level researches. Okay, so you might have seen many related to this research, right? MPPT in wind energy conversion system. So this is very important. Wind resource assessment. So based on this, if you look at wind resource assessment is very the first stage in this before installing any wind turbine. So normally it could be of a large area screening or field visit or wind measurement, data analysis or modeling, okay, by using a micro survey or micrositing. So these are the ways they are doing the wind resource assessment in India. And it depends on many factors, especially the topography and the height. Okay, so you know very well, right? If you are in Chennai, you know very well when you cross the Pundamalli flyover, you can see in the left hand side one wind turbine, right? So which is installed in one factory, right? And if you look at the windmills are not installed in all the places. It's not like solar. You cannot install in all the places. So it depends on the location. Okay, the location is very important. The location should be free from obstacle. Okay, free from mountains, free from the high-rise buildings. So this is very important. So that's the reason most of your wind farms, which is located in the rural areas, okay, it's not in the urban locations, okay, where the wind speed is very good throughout the year, and then only you can generate the maximum power out of it. Especially for the research is concerned, okay, for the electrical engineering or any other mechanical engineer. So you can do the research by using some software applications for the wind resource assessment, okay. So there are a lot of softwares available, but what they are doing, okay, what the wind power developers are doing is they are doing the wind data management, wind data analysis, atmospheric simulation modeling, wind flow modeling, then wind farm modeling, medium scale wind farm modeling. So these are the aspects they are doing it, okay. Regarding the software is concerned, so these are the softwares. But the industry, they have a different software. So they have their own customized software. But when you look at the researchers, what they are using is mostly the artificial neural network or artificial intelligence techniques, soft computing, and GIS based. Okay, so GIS based, you can see a lot of research papers available. Okay, so still they are doing the GIS based research. And when you look at the softwares for the colleges and universities research, so you can either use the MathWorks. They have the very good toolboxes available. I have shown the snapshots, and the computational fluid dynamics. Okay, so this is the another one, and you can use the research. Okay, especially for designing the turbine, for the blade analysis and the turbine stress, everything. So you can do this CFD analysis. Okay. So wind resource assessment, it depends on the height. Mostly when you increase the height, so the wind velocity will increase. So you can see the minimum, average, as well as the maximum wind speeds. Okay, so that depends on the tower height. So that's the reason why in the global scenario, the wind tower height is very high, okay, than in Indian scenario. And mostly if you look at the highest wind turbine, okay, so the highest power generating wind turbine, you might have seen in the General Electric, it is a 12 megawatt, and the height you can look at it is it's a huge height, right? So what the wind resource assessment finally they will do is they will do two things. One is annual energy estimation, and second one is wind turbine power curve. Okay, these are the two important aspects they will do it, and from this they will come to a conclusion. Okay, so whether we can install the wind turbines or not in this particular place. The other one is a wind farm development. As per the rule, initially they used a 5D and 7D rule for placing the wind turbines. Okay, so it's not like the fan which we are installing in our house or any other location, commercial places. So you cannot install in the straight row or column wise. Okay, so you need to have some distance in the horizontal as well as the vertical, as well as you can see that it is not straight line. So it's each wind turbine which requires the wind availability. Okay, so if you install the wind farms straight, so the second row you will not get the wind speed. So that's the drawback in this. And another area where you can do the research is now if you look at, okay, so we started in the year 85, and you look at the rotor diameter, it is 15 meter. Now you look at the rotor diameter in the year 2020. So we have reached up to 250 meters. So this is the drastic change in the research, and it is almost equivalent to wing size of Airbus A380. Okay, so you just imagine. So why we have gone up to this? Okay, so maybe for the audience, this is the question. So why we have gone for this much wing size? Okay, even if you look at the largest wind turbine, which is made by the General Electric, so they have this wing size. Okay, so the rotor diameter is also very high. Okay, it's purely because of this equation. So this equation is clearly telling you that the swept area A is very important. Okay, apart from your velocity. Okay, so the swept area, the more the swept area, the more the power generation. But even though the parameter A is not having much impact in the P power generation comparing with the velocity, but still it has the impact. Okay. So this is the same setup. You can see that 1980 where we are 15 meters, and 2020 where we are now 250 meters. And it is a single turbine with the 20 megawatts. So that's what the research has developed till now. Okay. And 1980, if you look at it, is almost, it's a 0.01 megawatt. Okay. So you just imagine the proportional thing. Okay. So 20 megawatt from 0.01 megawatt. So wind turbine technology option. So you can see that it is aerodynamic, then axis orientation, power control, yaw orientation, rotor position, type of hub, number of blades, and the rotor speed. So based on this, we can categorize the different wind turbine technology. So we'll look at one by one. So drag type wind turbine. So it is a very old Persian or Chinese model or 7 years model. Lift type wind turbine is the one which is you are able to see now, right? It's the horizontal axis as well as the vertical axis. Horizontal axis mostly it's a Danish type because the one which is they installed in the early 1985. So if you look at this purely based on the Danish concept, okay, you will see what is the Danish concept in the coming slides. So drag type, this is the sample. You can see that the Persian and the Chinese wind turbines, you can see that. So maybe the Chinese fisher net you might have seen in the Cochin beach, right? So the similar to that, you can see the same model, okay? These are all not having much commercially successful because the height matters and the power generation, okay? Whereas horizontal axis wind turbine, you can see in the left side and vertical axis in the right side, okay? So this is the difference. So horizontal and vertical axis. So we'll see the complete technical aspects in the coming slides. So lift, horizontal axis wind turbines. So these are the two models. One is onshore and another one is offshore, which is already explained in detail. Okay. Lift type wind turbine. So why this vertical axis wind turbine is not getting much popular? Still, you can find in some of the research stations. Okay, in some of the institutions, they are using this wind turbine for their research aspects. The only problem is it is located at the lower height and it requires a major maintenance aspects. Okay, and another one is its axis. Okay, so you see the axis length, and another one is the generation, power generation. Okay, from this is not quite maximum. Okay, so vertical axis, if you look at accepts accepts the wind form from any angle. Okay, and so the advantage is it's a ground level, but this has a lot of drawbacks. Okay, for example, wind is poor, there are self-starting issues. Okay, then the overall, if you look at the performance is very less and less reliable. Okay, and commercially it's not successful. That's the final point. That's the reason nowhere it is used. So drag and lift type to wind turbine, it's a short comparison with comparing with the 7 years and Dairy's wind turbine. So only 15% can capture it from the 7 years wind turbine, but the Dairy's wind turbine we already discussed. Okay, so more efficient than drag, but the problem is comparing with the horizontal axis, this is not having any successful. Okay, power control. mostly here we are coming into picture. Okay, so why the power control is very important, especially for low wind speed and high wind speed. So mostly there are three options they are using: stall and pitch and active stall control. Okay. Stalling is most important concept in the electrical machines, so which many of us might have studied in, as an electrical engineer. Okay, so stalling means just to stop the machine. That's it. Okay. So stalling is performed to limit the power output when the wind speed is very high, and when the low efficient when the it is in the low wind speed. Okay, so these are the ways they are doing the stall control. Maybe I will show you the graph so that what is a stall control. Okay, so the stall control you can look at, this is in blue color. So up to the rated wind speed, it is fine. Whenever it is going beyond the rated wind speed, you can see that the power output is slowly or gradually it is decreased. Okay, up to cutout wind speed. After that, this will be disconnected. Okay. Pitch control is another way you can control the wind power output. Okay, so mostly if you look at the blades, they are using this pitch control concept, and either by using the hydraulic option or some wind turbines they are using the electrical motors. Okay, so by controlling the individual blades, okay, so you can just adjust the blades. So this is to make the blades either to face the wind or to avoid the wind. Okay, so that either way you can do it. Okay. You can see that the pitch control, which is in the red color graph. Okay, so which is picking up, okay, up to the rated speed. Once it reaches the rated speed, even the wind speed is going beyond that. Okay, so the wind turbine is able to maintain the power output constant. Okay, so in this way, if you look at most of the researches in the paper, if you look at it's mostly the pitch control wind turbines. Okay, they might have used, and stall control, which is very old, and you can see the old wind turbines, this stall control concept. yaw orientation is the another one which is already explained. So but how they are doing this yaw orientation, because the top portion, nozzle portion, so they will try to rotate along with the direction of the wind. Okay, so this is very important because it has to face the wind direction. So that's the only thing. So this yaw motor, they are using it. Okay, either they are using hydraulic or electrical. Okay, so yaw orientation for the bigger wind turbines. Okay, megawatt wind turbines you can see in the left hand side. So like this they will rotate it. Okay, for few kilowatts, okay, you see the right hand side, the few kilowatt wind turbines. So normally it is automatically rotated because the inertia, the weight is very less, right? So this is the major difference. So comparing with the bigger wind turbines as well as the small wind turbines. Okay. The rotor position, you have upwind turbine and downwind turbine. So these are the two angles you can look at, which is facing towards the blades, and another one is in the opposite side. Hub type, where the mechanical engineer, they can play a very good role by designing this hub. Okay, so there are few types I have listed here: rigid, hinged, teeth. Okay, but in this there are a lot of research is happening still. Okay, so how they can design a blade so that it can even operate in the low wind speeds. Okay, the low wind speed is another research area where all the mechanical and electrical engineers you can focus. The number of blades, it's already explained. So what is the reason and why the numbers is 1, 2, and 3, and you can see the reason why, how fast it is rotating in the single blade, and how fast it is rotating the 2 blade, and how optimally it is rotating in the 3 blade system. Okay, and because of this reason, okay, so where optimally everywhere you can see the 3 blade system, still you can find the 2 blade system in Kaitar. Okay, Kaitar wind turbine research station. Tower, if you look at, there are 4 different types, but nowadays if you look at, mostly it is used tubular tower. okay, because which is very easy to manufacture in the factory, as well as you can transport it. And you might have seen a lot of trucks which is carrying the tower, okay, tower structures. So that is the most preferred one nowadays by the most of the industries. But still, I can show you the lattice tower as well as the tubular tower. So how it is looking different and how it is installed. Okay, tubular tower is very easy to install because you can install it in the blockwise. Okay, and but still you need some equipments in the site. So that's another challenge. Concrete tower, it is looks like this, but mostly it is not preferred by most of the industries. Guide tower is which is mostly used for measuring the or you can say that wind resource assessment. So that locations they can install, and every few meter height you can see that the measuring unit is there, and which measures and which sends the data to headquarters in Chennai, okay, in Nive. Architecture of a wind energy system, so it looks like this. Okay, so you have the multiple wind turbines which is connected to the common substation using the transformer, and which is transported. You can see that it's a transmitter and again distributed to the consumers. And sometimes you can use the capacitor banks for the compensation, okay, for the excitation as well as for the compensation purpose. Or you can go with the latest FACTS devices, okay, using a dynamic voltage or compensators you can use, okay. So this is the complete architecture of a wind energy system. In this, if you look at what are the engineers' role? Okay, engineers' role either in this wind resource estimation or aerodynamic, mechanical engineers, you can play a role like a gearbox. Then electrical engineer, you can play a role in the generator as well as the power electronics and transformer, and how to connect to the grid, as well as the control, overall control. Okay. So majority, if you look at the electrical engineers having a major role in this, and as well as the mechanical engineers, right? So being electrical engineer, if you look at, okay, so you might have studied the power electronics. So in the power electronics, you might have seen a lot of different converter systems, okay. So rectifier, then DC to DC, then DC to AC, that means the inverter. So all this topology you can use, but it depends on the generator what you are using it. Okay, induction generator means it's a different option. So I given the arrow. Okay, so in the arrow you can easily understand which are the converters is suitable for which generator type. Okay, so only the specific converters are suitable for the specific generators. So that's the one important thing. And especially the induction generator, which requires reactive power support, or you can say the excitation. Okay, so but whereas the synchronous generator and the permanent magnet, which is of not much importance. Okay, so you can go with the without excitation. So that's the advantage of going with the permanent magnet as well as the synchronous generator. And another thing is that for getting the for achieving the maximum power point tracking, sometimes some configuration you can use the DC to DC converter, which is same as your solar. Okay, solar also you are using the DC to DC converter, okay, boost converter to boost the voltage to match with the inverter input. Okay, so here also you can use the same concept, but only thing is that it is an additional converter which occupies the space, okay, as well as the cost. Generators of different types, induction generator, then doubly fed, synchronized, unsynchronized, synchronous generators. Okay, and topology, when you look at the Indian scenario, they used mostly the Danish type and the DFIG, and now the much popular direct drive concept. Okay, so the Danish type, that's what I wanted to say here. This is the one which they installed long back. Okay, still you can see it in some of the wind farms. Okay, for example, Kayatar, you can go and see this kind of wind farms are there, wind turbines are there still. Wind converter configuration, conventional without power electronics, induction generator with the fully fed, and induction generator with the doubly fed, synchronous generator with the electrically magnetized, synchronous with the permanent magnet. Okay, these are the areas where you can see a lot of papers and a lot of research is happening. Especially now, you can see our recent past, you can see the doubly fed as having that majority. Okay, and now slowly they are moving towards the permanent magnet synchronous type. Okay, So what is a direct connected electric generator, which is already explained, but in the picture you can easily understand very well. Okay, so the picture is clearly showing. You can see that the gearbox is a big, okay, and this is of induction generator, which is the stator is having a much bigger, right? And even though you have the gearbox, so this itself is the drawback. Okay, the gearbox itself is the drawback, because it requires the it is generating the noise, as well as reactive power is uncontrollable. It requires the soft starter or the capacitor bank. So that's the another problem, right? So this is the second type where you can use the slip ring induction machines, okay, as a generator, and here you can do the resistance control, okay, in addition to the existing configuration. Third one is by using the partial size converter. You can see the picture, you can understand. This is of gearbox, and you can see the stator. Whereas if you look at the converter size is very less, because the converter you are connecting to the rotor side. Okay, so normally you know very well the rotor parameters are very less compared to the stator parameters. So in this you have the lot of savings in size as well as the cost. Okay, and it does the same job, okay, as that of the another big size converters. So this is the full size converter where you can connect to the stator directly, and you can see here, okay, what is the size of the converter. Okay, the size of the converter matters now. Okay, but still if you look at which has the very good control over the generator, as well as it has a very good isolation, okay, in the event of fault. Electrically magnetized synchronous generator topology, you can see that which has addition to that, you need one AC to DC converter to give the excitation, okay, voltage to the rotor conductors. Okay, so that's the addition thing, okay, comparing with the previous one. But this has been replaced when you are going to use the permanent magnet. So that's the advantage of going with the permanent magnet. So you can avoid the excitation AC to DC converter. But here there is a one more advantage is this permanent magnet. Okay, so it doesn't it's a synchronous generator. It doesn't require as similar to the induction generator. So it doesn't require the reactive power support or the excitation. So you can see here it is a bridge rectifier. Okay, bridge rectifier means by using the diode. So that means a unidirectional converter you are using. In the previous cases you have seen bidirectional converter. So that means the power will flow front and back. But here you can see it's a unidirectional converter along with the boost converter. So boost converter will play a much role to maintain the voltage before the inverter, voltage source inverter. So, but if you look at the thing, so what is the important thing in this picture is the gearbox is removed. Okay, that's the much important thing. But whereas if you look at the permanent magnet, which is another challenge. Okay, so now the material research is happening, a lot of research happening in the material side. So the permanent magnet, how they can develop magnet of with a different material and cost effective material with a reduced size. So that is the common research happening in this field. So direct drive will be looking like this. Okay, direct drive is nothing but the one concept which is already used in the washing machines. Okay, washing machine, they are using the direct drive washing machine. So same concept, only here it is applicable. Okay. Because the washing machine, so what is the reliability issue is the belt. Okay, so the belt they removed now, and they have directly connected the motor with the drum. Okay, in the washing machine. So the same concept here they are using it. So what are the plus points and the minus points? So plus points I listed in the green, and the minus points I listed in the red color. Okay, so these are the configuration differences. But still, if you look at even some people, they are doing still the research on these topologies also. Okay, even though these topologies are matured. Okay, so there is a lot of research papers are coming now from Indian researchers. So grid integration, conventional and renewable dominated grid, this is the power flow direction. You can see that how the power flow is taking place. So the top one is without renewable, and bottom one with the offshore renewable. So you can see that the power flow is much exactly it's opposite. Okay, so So where you can use these renewables as a distributed generation stations, or you can use it for microgrid. Okay. This is a schematic diagram which I referred from the wind turbine research station. Okay. Power quality issue is already explained a lot, but I would like to list out only the few categories as far as India is concerned. Meteorological or geographical conditions like turbulence intensity, wind shear, fluctuations in the wind speed, and power production. So these are the main issues for the power quality. And another one is it is affected by the technology of the wind turbine you are using. So whether which turbine you are using it, DFIG or you are using a direct drive or you are using a Danish type. So it depends. Okay, so based on this, the power quality issues varies. And another thing is, you can see what are the issues related to the transmission sector. But whereas the government has already, they have initiated all the things. So there is a transmission corridor which is already happening. Okay, so how to evacuate the complete maximum power from the wind farms. Okay. But still, if you look at this, once this is in picture, okay, then you can see a lot of developments based on this. For example, if you look at hybrid energy storage with the energy storage, okay, then hybrid renewable energy, okay, then you can look at EV. You can look at the battery charging or EV vehicle charging, okay, or EV charging station. So all these things is depends on this. Okay, so once this complete infrastructure is in picture or in place, then this EV will develop gradually. Okay, and once the EV is developing, you can see that much more things will develop. For example, grid to vehicle or vehicle to grid, like that. So the basis is this one only. Okay. So power quality issues and parameters, especially which parameter is caused by which issue, okay, which is listed here for your information. Comparing the different types of wind turbines, these are the power quality related issues, okay. And when you look at the converter based wind turbines, it has its own compensation, okay. And another thing is in case of a fault, it can be quickly disconnected in case of converter based. And flicker is ignored in case of converter based, okay. But whereas the one important point is the harmonics, okay. So you have to maintain the harmonics within the limit as per the grid code. So we'll move on to the research. Okay, what is the priority for wind research, which is happening, okay, throughout the world? Okay, so grid system integration and infrastructure. This is the one part of research. So developing wind energy capabilities to fit a grid with a significant shares of renewable energy. Okay, so this is the one area, and another one is operation and maintenance. Okay, and third one is the industrialization. Okay, so it's about developing a value chain and facilitating the interaction. Okay, then another one is the offshore balance of the wind balance of the plant. So how you are exploring the new areas for the offshore wind and making it competitive. Okay, so that's another area where research is happening. And next generation technologies. Okay, so it's purely based on scientific research and to find out any other new technologies, for example flying wind turbines, okay, floating wind turbines, okay, or combined floating wind turbine as well as the tidal. Okay, so these are the some of the examples of the new next generation technologies. Advanced topics in wind turbine, if you look at as a researcher or as an engineer, you can do in this area: optimization, data fitting, wind resource assessment, estimation and prediction of wind and power. Okay, and regarding the control aspects, model predictive control is dominating now, adaptive control also, and then AI based control is slowly they are coming into picture. Okay, then optimization. So optimization means by using the soft computing techniques. Then another thing is the big data analytics and AI-based energy economics and market prediction, then promotional policies. So these are the another area you can focus, and which doesn't require any hardware. So that's the advantage in this. So this is also coming under the Sustainable Development Goals. Okay, one of the United Nations 17 Sustainable Development Goals are there. So you can do the research in this area. feasibility studies also you can do it. For example, hybrid, then energy storage, pumped energy storage along with the wind, then tidal with the wind. So these are the feasibility studies where you have a very good scope for the future research. Okay, most of the abroad universities, they started this research in this area. And another one is a computer vision based condition monitoring and surveillance system. So it's nothing but it's a remote condition monitoring. Okay, there is no need for a maintenance engineer in the site, and you can use this computer vision based techniques, and you can easily do the condition monitoring, even the prediction of the faults. Okay, so just before the fault you can predict and you can do this maintenance work. So that's the advantage of going with the computer vision based techniques. And other researchers, you can see that even you can use the data. So the data is very important nowadays. You take any field, the data is very important, because using the data, even you can predict the new fault. Okay, so this is what the new technology is happening now. Okay, so in fact, for this you need the big data analytics as well as some communication protocol. Then you need either cloud computing or any other storage mechanism. Then you need the real-time software. By using the real-time software, you can generate the reports and you can give the alert to the operators, or you can say it's utilities. In other area where you can find a lot of research is wind power big data, either wind farm side or turbine side or system side. Okay, for example, you can see in this big picture, so which is one of the research happening in the European university. And here what they are doing is they are combining all the generation side. Okay, then they are doing some smart grid or multi-energy analysis. Okay, and there one of the important goal is as per the sustainable development goal, they have to increase the deployment of the renewable energy comparing with the conventional energy. Okay, and they will do a lot of analysis. What are the analysis they can do, or you can, as a researcher, you can do is supply side data connection and data collection and system control. And another one is a demand side management. Okay, so demand side management, I hope this is a hot topic now. Okay, then electricity market, then efficiency management. Okay, so these are the other aspects you can do it, because the energy efficiency is one of the important word nowadays. There it is used in all the industry, so not only with wind energy. Okay, advanced topics, if you look at, okay, as a student level project, or as a mini project, okay, as a final year project, or as a research project, you can do this kind. Okay, because these are all small things. Either you can use some of the artificial intelligence techniques, or IoT, or big data analytics. So you can do this small you can take the small issues and you can do this. In fact, these many of these issues may not be there in India. Okay, maybe thunderstorm is the issue, but in Europe and other what is it other countries, if you look at where they have the temperature is going below normal temperature, that means 0 degree. So where you have the ice, frozen ice is the issue, condensation is the issue. Okay, so you can develop some mechanism which it can melt the ice. Okay, because if the ice is condensed in the blade, so what will happen, you know very well. So to avoid this, you need to have some preventive mechanism. Okay, like that you can work on advanced control technology. For example, dynamic thrust reduction, soft tower technology, anti-typhoon strategy. Okay, because the typhoon is now a big issue. Okay, especially for the offshore wind turbines. Then drive chain technology. Okay, different drive chain we are using. Okay, and intelligent yaw prediction system. So the prediction of the yaw based on the wind direction. So here also you can use some intelligent techniques. Then another one is MPPT, okay, based on the energy output. Then fine tuning the control, then yaw against the wind turbine, wind direction. Then soft cutoff, okay, during the high wind speed. This is another challenge. So in this area also a lot of research is happening. Torque controller, okay, at the rated wind speed. So this is another area where you can focus. And especially in the climatic characteristics, you can see a lot of things like ventilation flow, then electrical insulation, enhanced UV resistance ability, de-icing design. Okay, these are the areas that a lot of research is happening. So you can take one of this and you can do it. So which requires only the data. Okay. And this is the one which is done in Denmark, and which is nothing but they are using this wind for energy storage option. So they are using both pumped energy storage and this along with some other battery-based energy management system, energy storage. So whenever the wind is very high during that period, they will store the water in high mountains, okay, higher level. Whenever the energy is low, that stored water will be used for generating the electricity by using the hydroelectric power plants. Okay, so this is what the combined, okay, so wind power as well as the pumped hydro. Okay, so this is also coming into the sustainable development goals. So these are the areas where they are focusing now. Okay, most of the Europe as well as the US. AI in big data in renewable energy, for example, prediction. Okay, so there are a lot of AI techniques and big data they are using it, and deforestation maps they are linking. Okay, and weather modeling. Weather modeling is another challenge now. Okay, because the prediction mostly it fails. Okay. Then you can use the geospatial and sensor data for prediction for this wind turbine as well as for the solar. Okay, so in this area also there are a lot of research happening. So renewable energy and energy storage. Okay, so earlier we have seen pumped energy storage. Now we are seeing hydrogen energy storage. For example, by using the renewables during the excess generation. So what they will do, they will use this wind power or this electricity for generating the hydrogen from the electrolyzer. Then they will store it. Okay, and whenever the wind power or the solar is less, okay, so that time they will start using this hydrogen generation. Or sometimes what I can say is in a day, so whenever wind power is less, to smooth the wind power, to smooth the overall power output from the substation, you can use this hydrogen electrolyzer, or you can use the pumped energy storage, what I already explained, or you can use battery-based energy storage. Still, the battery-based energy storage is not viable because it's very costly. So there are a lot of researches happening in the um, what is it, developing the batteries, different type of batteries, and where it can store more energy. Okay, so that's the reason still it is under research. So renewable energy and the energy management. So energy management is another another good area where you can do a lot of research, like combining PV, then wind, and you can use some other utilities. Okay, and you can use some local loads, and by using the battery, so you can do some coordinated control, or you can do some different modes of operation also. Okay, in this also there are a lot of considerable academic research is happening. Okay. Then market analysis also another area where you can do a lot of analysis. The source is from the INL, okay, Idaho National Laboratory. So where what they are doing is they are doing some forecasting, they are doing the optimization, then simulation, and their integration. Okay. So this is another area they are doing this. It's purely based on the load forecasting. Okay, combined with all other. Okay, not only wind. So research in the Indian scenario, you can concentrate on grid integration and the power quality issues. Okay, there are a lot of reports already available for your information. Then energy storage option for the existing old wind turbines instead of the repowering. Repowering means replacing the existing wind turbines. So you can think about the energy storage options. Then feasibility of a hybrid solar PV with the existing old wind turbines. Also, when I was in VIT, I was participating in this. Okay, with the National Institute of Wind Energy and WTRS Qatar. Okay, so this system is now available. This system is now available. Okay, with the WTRS site. Then offshore wind resource assessment, which is already started, okay, in most of the places, and still you have the research by using the statistical and computing techniques, okay, as university researchers as well as the students. Then computer vision based remote monitoring, I already told, this is another huge area for the students, especially because most of the companies, they started this kind of research already in especially the wind as well as solar related companies. So you have a very good future opportunities. This is the one which I worked, in fact, in tie-up with the, what is it, Nive, okay. So I worked as a advisor, okay, for this project initially, and this is what the plan for them, okay, for the 200 kilowatt Micon wind energy generator. So they just want to connect the 75 kilowatt solar panel, and by using a smart grid controller to the nearby 400 by 11 kV substation, okay. But the future, maybe you can think about, okay, as of now, this solar inverter can be used to as a right throw, okay. Even for right throw also, you can use the solar inverter. But in the future, if you look at, maybe you can connect in the battery energy management systems, okay. In the college or labs, you can have this idea. For example, you can have a 1 kilowatt solar grid tie inverter to realize this research, okay. And you can have, for example, 250 kilowatt of 4 sets, okay, like a string inverter, for example, okay. The string inverter you can use like this, and you can connect to the common grid. And in this, you can connect 1 kilowatt wind grid inverter, okay. So small wind turbines you can connect, okay. The same also you can connect to the common grid. And these two you can connect with the battery energy storage, or you can connect to the laboratory PV panel, okay. So that student or researcher, what they can do is they can do some studies with the existing setup of 1 kilowatt wind and 1 kilowatt solar, and they can test their own circuit, okay, or their own experiment with that existing system, okay. And along with that, you can have this SCADA. Okay, so SCADA is a very good thing, and it's called as a central control monitoring center. So which collects all the information from all the resources as well as from the energy storage, and you can do some very good research analysis in the college or universities. Okay, so this is what I am suggesting to the different universities as well as colleges, if you plan like this. And this will not consume more money also, because I have given only lesser rating. So you can approach some industries or the companies, so they can install it. So the past is like this, and the present, they are concentrating on this. Maybe who knows, the future might be even the vehicle along with the wind turbine, okay. So EV with the wind turbine also, it's possible, okay. So with this, I really thank the organizers, IGEN as well as Panimalar, okay, college, for giving
Thank
me
you,
this
sir.
opportunity to share the research. And you can use this book. So I have published along with Dr. D.P. Kothari, so wind energy systems and applications. You can find all the informations, whatever I have shared in this, okay, as a detailed book. So one is available with the Narosa, and another one is available with Alpha Science UK. I also thank CWIT, Nive Chennai, and WTRS Nive Kayatar for their valuable support for me, and as well as given me the opportunity to participate in their projects. And I would like to share, I'm organizing few conferences, especially this one is a virtual conference, which is a free, and you can present the paper and get the certificate free of cost. And further, if you want to go for journal, there is a considerable open access fees. Okay, so this is the one, and which is on 9th July, deadline is 30th June. And this is another one, which is also purely based on the renewable energy, power electronics and renewable energy application. It's a IEEE conference. So the paper submission is extended now to 30th June. Okay, so you can still use this venue for your research. Okay, thank you so much.
Thank you, sir. Thank you, sir. It was a wonderful session. So we have one question. So with respect to this, what are all the factors we have to consider for the installation of the wind energy systems apart from the geographical conditions?
The factors you need to consider is energy density, sorry, air density. The air density is also very important. For example, if you look at Kayathar as well as the Nagarkovil, and if you look at Palladam, okay, and maybe Polachi, okay, so each location has a different air density. The air density is matters, so that also you need to consider, okay, apart from the topography. Topography means this obstacles, okay. So this is another important point where that means if you want to have a continuous power generation, as well as if you want to have some annual power generation. So if you measure that, so where they have the very good air density, so there you can find a very good output. So that's the key difference in this. And apart from that, the technology is also playing a very good role. So the technology means, I mean the softwares, what we are using it. So by using the software we can use, and you can easily predict the wind speed as well as the location. So that's the very important thing.
Thank you, sir. Thank you, sir. Thank you.
Thanks a lot, Uma sir, for joining us and enlightening us. And probably means we had 4 views. One is academic view, other one is a research view, other one is an industry view and employment view. I believe, I mean, so you are almost fit for all, because you're a professor from academic view, professor from a research view, and of course you have developed a renewable lab. So from industry view and employment view, I believe, I mean, what say, your session has definitely given insights of just not one perspective, but for all the 4 perspectives. Thanks a lot, sir, for joining us and giving us means wonderful session to enlighten us. Thanks
Thank
a
you.
lot, sir.
Thank you so much for giving this opportunity.
Yes, sir. Thank you. Now I invite Lavanya madam to introduce our next speaker. Lavanya madam.
Yes, sir. Yes, sir. All these sessions were very interesting. To make it more effective, we have our next speaker, Dr. N. Amudan, sir. He completed his PhD at Anna University in the year 2014, titled Grid Code Requirements and Performance of Adaptive Internal Model Controllers for Better Voltage Sag Ride through Indubly Fed Induction Generator Wind Farm. He received the Certificate of Appreciation from AMC Engineering College for outstanding contribution towards the overall development of the college in the year 2015-16. He has been honored and appreciated for the dedication and efficiency in carrying out his work related to National Workshop on Small Hybrid Power Engineering System DRDO project in the year 2012. Sir, we are indeed privileged in welcoming you to give your effective suggestions on the research view of the wind energy conversion systems. So please, sir.
Sir, you have to
Hello.
unmute.
Okay.
Perfect.
Thank you, madam. Thank you very much. Myself, Dr. Amudan from Rajarajasri College of Engineering, Bangalore. I'm presently heading Department of Electrical and Electronics Engineering. So already all the speakers spoke about the academic research and everything very deeply. So I'm going to shorten my presentation in going to shorten my presentation in research view. Can I share the screen, sir? Hello.
Yes, sir. You can go ahead. You can share in the bottom. You have an option to share it. You can share the screen, sir. You already co-host. You can share it. Yes, sir. Screen is coming up. Yes, sir. Perfect, sir. You can go ahead.
Okay. Now it's okay.
Yes, sir. It is okay.
Okay. Thank you. My topic is research opportunities in wind energy. So I'm going to present like this. This is my presentation outline. First, I'm going to start with a small introduction about why we want research in this renewable energy field. What is the importance? What it is going to give? Then the areas of wind energy research and what is the day-to-day state of art, and what is the international status and the technical barriers. What are the technical barriers we are going to meet in the development of the wind energy systems. After that, slightly I'm going to touch with the low voltage right through. That is an important part in the um, wind energy systems, very important part, and this is my research area also, and also future research direction, and somewhat important wind development in throughout the world also I am going to speak. And complete references about this presentation is given at the end of the slide. Okay. So introduction. So okay. So first, why we want to go for this renewable energy research is it should contribute to the climate change, and it should be a carbon neutral, and it should enhance the livelihood strategies. So why it is required means the women in India, sorry, the women in India regularly spend between 2 to 7 hours each day collecting the fuel and cooking, like that. Okay, so that they can utilize for some other better works. Okay, and in rural sub-Saharan Africa, many women carry 20 kilograms of fuel wood and average of 5 kilometers every day. Okay, this time they can spend in another works like child care, education, and socialization and income generation, like that. Okay, that is the main problem. And in in energy services, okay, about 1/4 of the global population, 1.6 billion people have no access to electricity, and 6.4 billion people rely on traditional fuels such as wood, charcoals, or dung as their principal source of energy for cooking and heating. Traditional fuels are literally killing the people, as 2.5 million women and children die each year through indoor air pollution from cooking fires. Okay, this is one of the main observation. It is not a news or a paper news. This is came in journal itself. Okay, and also there is a important point came in journal related to this wind energy. It is observed that in India, when the highly favorable assumption, the designation of wind energy of power generation is likely to reach its maximum utilization potential in another 20 years. Okay, that is what that prediction says. The growth trend of wind power development in 6 Indian states indicate that more than 90% of wind energy potential in India can be exploited by 2030. Okay, that is also important point. Because of this, the people are moving towards the low wind speed turbines and hybrid wind turbines, microgrid, and other things. Okay, that is also one of the main area we have to concentrate. Okay. So proudly we can say India is the first country to have ministry in the field of renewable energy. It is started in 1992, Department of Non-Conventional Energy Sources, and become Ministry of Non-Conventional Energy Sources, aim to research and develop renewable energy sector. And that we know very well, it is a multifaceted and interdisciplinary research, and it completely freely available. And it is a very rapidly developing area. Mainly the running cost of this renewable energy power is negligible. That is what, because of this fuel and other things are naturally available, the running cost is very negligible compared to conventional fuel systems. Also, the extraction of power from wind is cheaper than the solar energy. That is the main reason the wind energy is preferred. Actually, it is very cheaper compared to solar energy. It will occupy very less area, and also, but the main restriction it is based on the geographical area. It will work. Okay, so that is the main limitation. But compared to solar energy, it is very cheap. Okay. So and another one main problem is it is mainly located in far away from the load center. So because of this, we have to transmit more power from the one place to more distance. We have to transmit the power. So because of this, the main problem associated is fluctuation and voltage sag right. Okay. So these are the things we are going to analyze. And before going to the research, we have to see what is the main history of this wind energy generation. So I'm going to review small wind energy history. This is also available in journal. Okay, the reference is given in the at the end of the session. Okay, so first it is we used in agriculture mainly we used, and first the USA government involved in wind energy research in 1973 after the oil crisis. Okay, after that it started booming up, and after that in 1973, the following in the year 1973 and 1986, the commercial wind turbine market evolved from domestic to agriculture with the 1 to 25 kilowatt utility interconnected wind farm applications, and it is around 50 to 600 kilowatt. In this context, the first large-scale wind energy penetration outbreaks was encountered in California. Okay, this is the beginning of the history, but this is 2000 years back. Wind energy have the long history, more than 1000 years. Okay, and this is developments happen in the wind energy systems. It will be used in pumping water, electricity generation, different milling the grain, like that. So many types of wind energy towers and turbines they developed in day by day, and this is our trend of the wind energy development system. So it will be first started with in 7th century person windmills, rotation through aerodynamic drag, and then touch windmills they emerged, and now this is the 20th century wind turbine, and again 21st century the wind turbines completely connected with CBS system, that is cyber physical systems. So the main areas we can concentrate on research is turbine research. That is a very promising area because the large scale, large wind turbine, small wind turbine, the turbine designs, everything will be. So it will only extract the power from the wind. Okay, so it depends on the wind turbine only. The performance of the wind, the output will vary. Okay, so for that reason, this is a very promising area of research. That is aerodynamic designs, flow of turbulence, everything we have to consider, and it should be low cost also. And the second main area of wind research is wind resource assessment. Okay, so it involved with feasibility study and everything. So which area, if we particular area, which direction we have to install the wind farms so that we can get maximum efficiency. And the forecasting also very much important. So here we can use some weather radars, okay, Doppler radars, and predicting the wind speeds and patterns and airfoils, everything will come in this forecasting sessions. And also the utility grid integration, that is also the next part of the research area. It can be it should be connected to the grid so that we can distribution is very easy, and it required new techniques and models to and the grid operation also. We have to see separate energy management system also they are developing for renewable energy sources. Okay, so that is another one emerging area, one very promising area in the wind energy research. And after that, energy storage. Okay, we can use some chemical fuel cells or hydrogen energy to store the energy, and we can utilize. So sometimes they'll use mechanical flywheels also. Okay. And this main state-of-art research is based on wind turbine design, wind farm development, and wind farm operations. So in this wind farm designs, they'll concentrate on blades, towers, and nozzles. Blades, towers, and nozzles. And in that, they'll in the blade, they will manufacturing of the blades, composites, material and modeling is the main part. And the nozzles, they will concentrate on gearbox, rotors and generators. And the wind farm development, they will see the offshore installation and siting, then flow characterization of loads, waves and wind. And the next part is wind farm operation. They will concentrate on controls, power production, and structural health of the wind tower, and the sensing, diagnosing, testing, and relay. All these things they will concentrate, and finally energy storage and transmission. Okay. Then this is internationally. There are so many people are available. To manufacture wind turbines. So these are some of the promising wind turbine manufacturers. So the first place given to Vestas and the last place given to SE Wind. So you see the curve how the 2015 the turbine manufacturing market and also the 2017 manufacturing market in the EU. Here, the main part is the technical barriers. What are the main challenges we'll face in the wind farm generation? The main part is lack of infrastructures and operation and maintenance, and lack of R&D capabilities and technology complexity. Because it is a multidisciplinary research area, it is always complex to integrate with one part to other. Okay. So that is the main challenge in the wind energy development. So mainly in India, what is the problem is our technology, our wind turbine technology is completely based on European technology. So Indian market lacks of local standards in turbines. Okay. So mismatch in the self-manufactured items and imported component is likely to occur. Also, modern wind turbines are quite efficient, but when the wind farm is concerned, the performance of individual turbine is advisory, affect the other turbine also. Thus, overall wind harnessing efficiency of wind turbine is less than could have been achieved if all the turbines were individually and independently functioning. Okay. And here, the another one big barrier is the mechanical part. Okay, mechanical part of the wind turbines have more failure than the electrical part, and the reliability study is very important because of this. Because the first year operation and the fifth year operation will vary drastically, and it will reduce almost 30% from the first year to fifth year. Okay, that is the main reason. The reliability study is very important and the main technical barrier in the wind farms. Okay. So sometimes what will happen, it is not possible to for grid to absorb wind generated electricity when the penetration levels are very high. Okay, due to this reason, wind farms of Tamil Nadu used to remain shut when the generation was reaching peak, and thus loss of useful energy occurred. Okay, so that is also main reason. And you see some small data they given in 2017-18. They generated power about 12 billion units compared to 2016-17. That is only 7 billion unit of powers. Okay. So why? Because means now the techniques they improved, and the forecasting, scheduling, everything they included in this, and the monitoring stations need to be daily basis metering arrangement they arranged. Everything, some technical advancement happen in the renewable energy field. Because of it, they achieved 12 billion units of powers. So the main future direction of research is it will be improved models for operation and extreme structural loads. That is the main part we have to concentrate, and also dramatically better method for considering soil structures interaction, subsurface effect of structural performance, rationalized and streamlined design procedure for floating systems, and increased construction and installation capability for offshore systems generally, and risk-based framework for performance assessment of offshore wind structures, and demonstration project to prove numerical methods and environmental challenges. So these are the main direction of research going on. And in that, the main part is low voltage right through. Without the low voltage right through, this wind energy research will not fulfill. Okay. In this LVRT, they will mainly concentrate on grid variables and turbine variables. In that, they will, in the grid variable, they will use voltage during fault, voltage overshoot and recovery, and response times. In the turbine variable, they will consider rotor speed and the rotor current, and then the DC bus voltages. Okay. And this problem, there are a lot of solutions are available in LVRT problems. That can be all these methods will comes under these 4 methods. Okay, so we can coincide all the methods. Thousands of methods are available. All the things we can coincide with this method. That is, first one is the direct axis and the quadrature axis current of the rotor. The second one is torque speed control and hence MPPT via direct rotor current IDR. And the third method is reactive power exchange. And the fourth one is external voltage support. Okay, so these are the within the 4 methods available to overcome the LVRT problems. Okay, so each one have different methods. Okay. First one have so much of subdivision, and the second one having so many methods like that. So we can control the direct axis and quarter axis. We can control the torque and speed, and also we can control. We can give the reactive power exchange. So for that, we can use other methods, and also the external voltage support. Also we can give. Okay, that is the main part. So some of the methods available based on this, this is given here. That is, first one is rotor current control and the MG set connected to the flywheel. That also another one method. And chopper in the DC link. So here you see this diagram is in the IEEE. They given how the chopper is connected in the DC link to improve the voltage sag right through problems. A slightly modified chopper is included in this DC link of back-to-back converters, and that performance they study. Okay, and also there are some more things are also available, like series dynamic breaker resistor and TCSC connected wind farms and series grip side converters. Then SATCOM and SVC based wind farms and magnet energy recovery switch connected wind farms and DVR connected wind farms, and wind farm connected to grid with series compensator, superconducting fault current limiter, and superconducting magnetic energy storage. These are the methods already proposed in various papers to overcome the LVRT problems. So and the next promising area is wind turbines installed in the high-rise buildings. Okay, this is a very promising area going on now. Even in cities, they are planning to install wind turbines in between the towers as well as in the top of these towers also. The main promising problem is the vibration. So because of the vibration, it may collapse the building. Okay, so that problem still under study only. So they are expecting very prominent solution for this vibration problems. So here in the high-rise building installation, mainly they are facing 3 type of problems. That is, the influence of wind incidence angle and the concentration ratios are most significant in this. Also, because of even small variation in these parameters have a significant effect on the wind power takeoffs. Also, the influence of turbulence intensities, tunnel opening, and the constellation location is relatively moderate. An increase in the tunnel section area of the entrance would adversely affect the efficiency of the wind power generation. This is BWTC a tower which is installed with wind turbines. Okay, so this is also one of the major focusing research area. Now with the low speed wind, they started developing low speed wind turbines. So mainly concentrated on city high-rise buildings and where the flow of wind speed is very less. This is another one promising area, which is bionic wind turbines, highly developed wind turbines that is based on bioengineering. That is, bio-inspired wind turbines are available now. They design that is called bionic wind turbines. So this is one of the focused area in wind turbine research, because they are claiming that we are going to override this BETS limit also. That is 59.3% also we are going to override, and they are going to give the efficiency as more than that. Okay. So this is one of the main research area. So here you see the improved airfoil increased to 8% the standard blade, and also partially improved airfoil, it increased the efficiency at 10.2% than the standard blade. Okay. So this is a bionic wind turbines which is available. Okay. Then there are a lot of potential area available, that is micro turbines, completely based on low wind speed also they are developing, and offshore wind turbines, that is also another one area. Bladeless wind energy wind turbines also available, and doubly-fed wind turbines, this is already very so many researches going on throughout the world, and super fans, that is also available. Micro and nano grids, underwater wind farms also they are developing. So this is the first developed underwater wind turbine. Okay. Okay. So see, this is some of the main research areas we can concentrate. Also, there are the LVRT research, that is the main part in the wind energy generation throughout the world. All the countries developed their own wind grids code for the LVRT, and depends on that it will vary. All the previous speakers explain more about this. So I'm also slightly telling about that. That is the very promising area of research throughout the world. With proper grid code, we can grid code. The research is going on, and so many. So many opportunities also available in the LVRT research. So this is my reference point. Okay, so up to this, so I am concluding my presentation. Thank you very much.
Thank you, sir. So we have a question from the researcher actually.
Okay.
So he's expecting some name of the funding agencies who is supporting the researchers.
Sir, so many research areas, research funding agencies are available. Mainly, MNR is the main funding agency in India, and apart from that, CPRI, and even DRDO also funding. DRDO, CPRI, CSIR. So many people are funding for renewable energy research, particularly. And apart from that, international agencies also available. Royal Society of Engineers, like that. So many research funding agencies are available. No
Thank
problem.
You, sir.
We can.
Thank
yeah.
you, sir. Yeah. I hope his question got answered. Thank you.
Thank you very much, sir. The session is a eye-opening session for the budding researchers, those who are interested in doing research in the wind energy. Thank you very much for a wonderful session, sir. Thank you.
Thank you.
Yes, sir. Thank you, sir. You can now stop sharing the screen. So we are going for a final concluding remarks for the overall day.
Okay. How to do that?
Sir, you can just press stop screen. Otherwise, I will do that, sir. I will do that. Not a
Okay,
problem.
okay.
Yes, sir. Hope now.
Okay. I think
Yeah.
it is over.
Yes, sir. Yes. Fine. So, very good evening or very good afternoon, everyone. So today also we have missed a time. We are extremely sorry for that. But that session is probably we have to cover from all the 4 perspectives. That's a little time which we have consumed. Anyway, so I'm just giving you an overall view of 2 second day program. So we have started with engineer Sriraj Balakuru. On the employment perspective, he has talked about the employment opportunities in the wind sector. And the session has been carried out by Amuda on industry perspective of the wind energy conversion system. Then we had Dr. Uma Shankar. He's an associate professor. He has talked about the academic perspective of wind energy conversion systems. And of course, he has touched, it's a research perspective as well. And finally, Dr. Amudan sir has given a very good overview of what are the research, funding agencies, etc. So with that, we are winding up day 2. But means I have few quick important updates for the participants, those who are joining on YouTube. You have 2 interesting options to talk about. One means we have an interesting cash award that is by our engineer S. Sendil Kumar, AE TAN Transco. He is providing a cash prize for the surprise prize for the peoples, those who are consolidating and sending the reports to the email ID IGEN-FDP.com. So please make a note of that. Probably that email ID, you can find it after the session in the comment box as well. The email ID is IGEN-FDP@gmail.com. That's the email ID which you need to send your consolidated reports on a daily basis. On 4th day evening, we will be consolidating the best reports and we will give a cash award for the best reports. And we have another interesting, fact. Means if you have some good questions or answers or some points or suggestions which you are making, you will be brought inside the, so directly with this faculty development program with the eminent speakers on day 4 and 5. So that means if you are effectively interacting with the in YouTube chat box, you will get an option to join us directly on day 4 and day 5 in Zoom itself. So let me quickly repeat. You have an interesting 2 competitions. One is you need to write the consolidated report of what you have learned on a daily basis. On daily basis, you have to send that to the email ID IGEN-FDP, IGEN Faculty Development Program, IGEN-FDP@gmail.com. That we will be evaluating on Thursday evening, and the winner will receive a cash award which is offered by engineer S. Sendil Kumar, AE Assistant Executive Engineer TAN Transco. And based on your effective contribution in terms of questions, clarifications, answers in YouTube chat, you will be invited for day 4 and day 5 along with the eminent speakers. So with that, before I'm concluding, I will remind you what's the session tomorrow. Tomorrow we have an interesting session on day 3, on unit 3, that is a solar power. When we say solar, we are going to cover both the PV and concentrated solar thermal. So academic perspective, Dr. S. Selvi, he is a professor and head from Panimalar Engineering College. He is going to talk. And then industry view, we have an eminent person, Engineer Balakumar. He's manager engineering and design power projects. He's going to talk about the engineering perspective of how the solar plants are designed, grid connected and standalone, including some simulations. And I'm going to talk about employment perspective. And finally, we have a Dr. Padmavati K. Yeah, we have Dr. Padmavati K, Professor, BMS College of Engineering. She is going to talk about the research perspective. So that's what we have tomorrow. And what's the unit 4 and 5 is coming on. We have an eminent speakers and we are planning for some surprise speakers as well on day 4 and 5. So please stay tuned, stay connected. And I probably thank all the peoples, those who have joined as a speakers, those who have joined as a organizers, or those who have joined as as a participant in YouTube. I once again thank everyone on behalf of IGEN and Panimalar. Today we are winding up with this now, and we will meet again sharply at 9:55 a.m. tomorrow. Thank you. Have a nice day.